This conference will now be recorded.
Good morning, everyone. My name
Good
is
morning.
Srinivas. I am the founder of the VLSI Guru Institute. Uh, so today we'll be starting with the USB4 protocol training. So first, let me start off with the course overview. The course will be for 6 weeks duration, and it can stretch by plus 2 sessions as required. Because USB is a vast protocol, we have to cover it starting from USB 2.0. Hence, it might end up extending to 7 weeks overall. We will, in this course, we'll get a very, mostly the course will be protocol training focused only. There will be 1 or 2 sessions where we'll only talk about the basic test bench development concepts. Otherwise, majorly it will be a protocol oriented course. From a participant's perspective, mostly basically it is what I'm trying to tell here is, do you want to learn it over 6 weeks or 1 year? Let's say if you are planning to learn it over 6 weeks, you need to read the spec, complete the assignments in sync with the trainer session. You will see that things will move very quickly. Probably today we'll be completing USB 2.0, we'll be taking a quick overview of USB 3. And then for next few weeks, we'll be going over all the layers of USB 3. It could be topology, it could be the enumeration concepts, it could be the different layers, protocol layer, link layer, and physical layer. You will see that things move very quickly. Probably whatever happened this week and what we are going to do in the next week, there might be a significant difference in that. So I want you to be completely focused for this 6 weeks duration or 6 or 7 weeks duration. Make sure that you read the spec, you complete the assignments in sync with the trainer flow. That will ensure that you are able to complete the course in 6 to 7 weeks. If you are not able to do, then it is going to take again a significant amount of time. Once you miss the topics, once you miss sync with my flow, again you going back to those topics and revising is going to take significant amount of time. So please make sure that this 6 weeks, if you plan to enroll for the course, you spend dedicatedly a lot, at least 3 to 4 hours of time every day for USB 4. And trust me, it is worth it, not just because you're going to learn USB 4, because you're going to get familiar with all other high-speed protocols. There are a lot of things that are common between USB and other protocols. It could be in terms of the OSI reference model kind of modeling that is used across these protocols. It could be in terms of how the packets are framed, how the link management happens, how the error handling happens, how the interrupt handling happens. There are many things which are common across the high-speed protocols. So whatever 2 months you are going to spend, October and November, that would be a very significant time for you, where it will give you exposure to how very high speed protocols work. And most of those concepts will be quite applicable to other protocols as well, and it would make it easy for you to learn PCI Express and any other protocol for that matter. So you would probably realize at the end of this course that once you learn USB, you can easily learn PCI Express yourself by reading through the spec. Now, the reason I believe most of you are joining this session is because you feel that the USB spec is quite long. It runs into almost 550, 600 pages. Now, if you take USB 2.0, USB 3, and USB 4, it's even bigger. And of course, there are a lot of things common across these specs. But still, you feel that, reading through those many pages is a significant task. But once you get familiar with USB protocol, how it works across the various layers, the similar effort would not be required in any other protocol. Okay. So in summary, what I want to say is you please dedicate next 2 months time only for learning USB, of course along with your office work, but take out some time. So that is from a participant's perspective. So we will be giving assignments for every session, so please make sure that you complete those assignments. That assignments will make sure that you have to read through the spec, you have to refer to the internet and find answers. So that will ensure that you get into the spec and you start reading individual aspects of the product. So this will be the agenda for our course. We will be starting with the USB overview. Then we will understand basic protocol concepts. Then we'll start with USB 2.0. Then we'll understand USB 3.x. And when I say 3.x, I'm talking about 3.0, 3.1, 3.2. There we'll talk about architecture overview, data flow model, how data flow happens, transaction flow happens in USB 3.x. And the significance of protocol layer and the features, detailed features. Same thing for link layer and physical layer we'll talk about. Then USB 3.2 device framework, and then we'll talk about power management, error handling, all the miscellaneous aspects. Once it is done, then we'll talk about USB 4, where we'll talk about configuration layer, adapter layer, transport layer, and USB 3 tunneling, the interoperability with Thunderbolt 3. Majorly, if you ask me, where is that we are going to spend considerable amount of time is USB 3.x. Even though my training heading is USB 4 protocol training, but you will realize that USB 4 doesn't do any significant changes in terms of the protocol behavior, the device classes, the packet types, how the link management happens. There are almost 10 to 15 features which defines what is USB. They don't change from USB 3.x to USB 4. What it does majorly does is it introduces this adapter layer and configuration layer, which helps USB to work with various other technologies like DisplayPort, the PCI Express, host-to-host tunneling. This concept is what we call as tunneling. So the tunneling it enables us to do. Otherwise, all the basic concepts that are there in USB 3.x will be applicable to USB 4. But when you come from USB 2 to USB 3, there is of course a significant change in terms of the overall architecture. The way the USB 3 architecture has been divided into multiple layers: protocol layer, link layer, and physical layer. In USB 2, we didn't have so many layers. We only had protocol layer, and then we had one concept called as UTMI. So these were the things that were there in 2.0. But since our focus is on more on USB 4 and all the fundamental concepts are from USB 3, hence we are going to spend significant amount of time on USB 3.x. So at times you may feel that I'm going quick with USB 2.0. Please expect that, because the USB 2.0 itself is quite in depth. I mean, if I have to spend explaining each and every topic in a very in detail, it is going to take in itself another 3 weeks. So which is not going to give us enough time to discuss on these aspects. So hence I'll be a bit quick with USB 2.0. Having said that, I don't expect any one of you to come with any prior USB knowledge. So I will try to make it as easy as it possible to make sure that you are able to understand things. So now let's start with the USB overview. So what is a USB? USB stands for Universal Serial Bus. Basically, USB is a cable bus connecting, supporting data exchange between a host computer and a wide range of simultaneously accessible peripherals. So it is called as Universal Serial Bus because it supports wide range of simultaneously accessible peripherals. What is meant by simultaneously? It is possible for the host to communicate with multiple devices at the same point of time. In the same frame it generates, it can target device 1, it can target device 2, it can target device 3. That is what it means by simultaneously. When we say wide range, we are talking about different types of applications. It could be a printer, it could be a music player, it could be a mouse, it could be some kind of adapter, anything, it supports everything. And all these are peripheral devices which are connected for peripheral applications. And what is meant by universal? Since it supports wide range of peripherals, it's called as universal. And it is called as serial bus because data transfers happen in serial manner. And USB standard is maintained by USB implementers forum, which in short stands for USB IF. There have been 4 generations of USB. It started off with USB 1.x, then we had USB 2.0, then we had 3.x. When I say X means 1.0, 1.1, 3.0, 3.1, 3.2, and then we have USB 4. So overall, if you ask me how many such generations were there, 1.0, 1.1, that is 2. This is 3. Here we had 3, another 3, 6, and 4, 7. Totally, USB standard would have been released totally 7 times. So now, how the overall finally USB 4 has evolved and when the USB 1.0 was released. USB 1.0 was released in 1996 and USB 1.1 was released in 1998. So it was only supporting low speed. It supports low speed and full speed 1.1. And in 2000, USB 2.0 was released that supports low speed, full speed plus high speed. Then USB 3.0 was released, which supports super speed. When I say only super speed, I don't mean only super speed. It supports backward compatibility also. It would support high speed and full speed as well. And USB 3.1, which was released in 2013, supports super speed plus. I will explain the difference between super speed and super speed plus as we go forward. Then in 2017, the USB 3.2 was released, which is also super speed plus. Then in 2019 August, USB 4 was released, which works up to 4 gigabits per second and it uses 2 lanes, multi-lanes. And USB 3.0, this one, which was released in 2008 and which works at super speed, is also referred to as USB 3.1 Gen 1 because 3.1 came and it is the generation 1 of the 3.1. Or either you call it as 3.0 or you call it as 3.1 Gen 1. Or in terms of USB 3.2, it can be called as 3.2 Gen 1 Cross 1. Why this is significant is you may be thinking why so much confusion? Why can't we just go by 3.0, 3.1, 3.2? Many times in the spec you will come across this line. Many times in the spec you may come across this thing. So you should not get confused that these 3 are different. These 3 are essentially the same standard. When we talk about 3.1, it is referred as 3.2 Gen 2 Cross 1. It is the generation 2 Cross 1. And what about 3.2? 3.2 includes 2 things, USB 3.2 Gen 1 Cross 2, Gen 2 Cross 2. So we will talk about all these aspects. What does Gen 1, Gen 2 refers to here? What does Cross 2 refers to here? Everything we'll talk about as we go forward with the course. Right now we are just talking about how the USB 4 has evolved since it was released in USB, basic version of USB was released in 1996. Can you please take a look at this table once? So it talks about the specification, name, what was the previous name, USB interface branding, and what is the data rate it supports, what is the transfer speed we get out of it, and what is the logo that is used for it. USB 3.0, the name is 3.2 Gen 1. And it is USB 3.1 Gen 1. Previously it was called as 3.1 Gen 1. And the branding is super speed USB 5 gigabits per second. Basically, the whole intention, if you see in this chart, what you will see is the speed is doubling 5 it becomes 10, it becomes 20. When you go to USB 4, it is becoming 40. So with every generation, you are doubling the speed, 5 to 10, 10 to 20, 20 to 40. Now, if you ask me, was it the case in USB 2 also? USB 2 used to work at 480 megabits per second. So, which is not 10 times, which is not 4 times. It is actually essentially we are achieving almost 12 times or 10 times. So, this is the only exception. Otherwise, when you go from 3.0 to 3.1, 3.1 to 3.2 or 3.2 to 4.0, we are essentially doubling the speed, data rate. Data rate is 5 gigabits per second, and the effective transfer speed is 500 megabytes per second. So you may say 500 gigabits per second doesn't translate into 500 megabytes per second, right? 5 GBps is not 500 megabytes per second. It is due to there is a concept called as 8-bit 10-bit encoding will be there. Effectively, due to this encoding, you lose 2 bits. For every 10 bits, you are losing 2 bits. So what you are left with is, even though it is 5 gigabits per second, you are effectively getting only 4 gigabits per second. The effective data rate is only 4 gigabits per second, which is nothing but 4 into 8 is 500, I mean 50, which would essentially come to 500 megabytes per second. Whereas when you come to 3.1, which was previously called as 3.1 Gen 2, and after release of 3.2, it is called as 3.2 Gen 2. The branding is USB 10 gigabits per second. It gives a data rate of 10 gigabits per second, which would essentially result in 1.21 gigabytes per second. Again, you may not be seeing the same relation that you see here. I mean, if I divide 8 gigabits per second, 8 into 8, effectively it should give 64, right? No, 8 into 4 into 8, 50. No, 4 into 8, 32. 4, sorry, there is a mistake I did. Here I did 4 into 8, that's a mistake. I should have done 4 divided by 8, which would effectively result in 500 megabytes per second. Here, if you divide 8 gigabits per second with 8 to convert it into bytes, you get only 1 gigabyte, right? You get only 1 gigabyte, but you are getting 1.21. The reason is, here when you come to super speed plus, here, these are all super speed plus. We are going to use an encoding scheme called as 128 bit by 132 bit encoding. So more about that I will explain when we go to 3.0, 3.1 and 3.2. Let me just give you a quick notes. Yeah. So it's a 6 weeks, 3.5 hours session. When it comes to notes, technical aspects. So USB 3.0 under super speed. USB 3.1, 3.2 are called as super speed plus. Okay. It gives 5 data rate of 5 gigabits per second. It uses 8-bit NB encoding. 8-bit NB encoding. So that means for every 8 bits of data, we are encoding it into 10-bit format. So you are essentially reducing the the bandwidth will reduce by 20%. So effective transfer rate will be, effective data transfer rate is 4 into 0.8, no, 5 into 0.8, which will come to 4 gigabits per second, which will translate to 500 megabytes per second. When it comes to USB 3.1 and 3.2, the data rate is 10 gigabits per second. In the other case, it is 20 gigabits per second. So here we are going to use 128B by 132B encoding. So for every 128 bits of data, we are encoding it into 132-bit format. So effectively, we are consuming 4 bits more for every 128 bits. So what is the effective rate will be? Effective data rate is, it will be 10 into 128 by 132, which you will see that it will come down to 1.21 gigabytes per second. It will effectively come down to 1.21 gigabytes per second if you do this calculation. In the other case, you will get 2.42. So this is the logo which is used for 3.0, 3.1 and 3.2. The number 5, 10, 20 shows what is the generation we are working at. When you come to USB 4, the logo looks like super speed won't be there. There will be this kind of thing will be there. There will be one kind of half circle kind of thing will be there, which will tell that it's a USB 4. This is how in the down you can see how the ports looks like. Micro USB AB, micro B type B port, USB type A, USB type B, USB 3.0 type A, USB 3.0 type B. So different ports, which I believe currently is not so much significant for us, because we are not looking at mechanical aspect. We are more looking into the protocol aspects. So probably as you learn, you'll realize why it requires this set of ports. All those things will be much familiar. You'll get familiar as we start getting into the individual aspects of the USB. So this is about USB overview. So before we go deep into the USB, let's understand some protocol basics. As I said before, I don't expect you to come with any kind of basic protocol knowledge. I mean, having exposure to any protocols like SPI, APP, or I2C, any kind of such basic protocols is an added advantage. However, the training will assume that you don't have much exposure, and it will start from the very much from the fundamentals. So one of that aspect towards that is understanding the protocol basics. So there are two types of protocols. One is on-chip communication protocol, one is peripheral communication protocol. So USB falls under peripheral communication protocol because it is interfacing our chip with the peripheral components. So the first category of protocol is on-chip communication protocol. The examples are like AXI, AHB, APB, Wishbone. In on-chip protocols, there is no restriction on the number of ports connecting the master to slave, because the fabrication technology is so advanced that there is no restriction on number of pins. You can have a data bus of width 64 bits, address bus of width 64 bits. Even though all the AXI ports add up to 200 pins, the fabrication technology is so advanced that that whole thing can be manufactured in few micrometers. That whole 200 wires can be manufactured in few micrometers space. Hence, there is no restriction on the number of ports. What is the limiting factor of the on-chip communication protocols? The frequency of operation is the limiting factor. The frequency of operation is limited, I would say limited, due to the timing closure requirements and signal skew. See, as a functional verification engineer, you don't really come across timing closure in our day-to-day job unless we run gate level simulations. We don't hear the term timing closure, but from a back-end engineer perspective, physical design engineer and STA engineer perspective, the timing closure is a very important aspect. So timing closure is a very important concept, a very important aspect for them. As the frequency of operation increases on the chip, the closing setup time for various aspects of the chip becomes more and more difficult. So that is what limits the frequency of operation in the on-chip communication protocol. Now, when we go to peripheral communication protocol, what is majorly that limited by is number of pins. You cannot have peripheral protocols with a large number of pins because they will end up consuming bigger space on the chip, on the electronic device. Hence, they are majorly limited by number of pins. Again, we can divide peripheral communication protocols into two categories. One is high-speed protocols one is low speed protocols. First, let's just talk about low speed protocols, then we'll get into high speed protocols. See, the low speed protocols are meant for low data throughput. Something like SPI, something like I2C, something like UART. These are all meant, I mean, our intention itself is to get a low data throughput. Why do you want to get low data throughput? Because the applications for which you use I2C, SPI, UART kind of protocols, let's say it could be some sensor data. There is a sensor, we are reading some data from a sensor. You are not going to get some megabytes or gigabytes of data, right? You are going to get few bytes every second, probably. In those cases, you don't need to go for complex high data throughput based protocols. I2C, SPA, and UART kind of protocols would be sufficient for that. So those kind of applications are what I'm calling as low data throughput applications. In those cases, our intention is majorly to keep the circuit simpler, keep the power consumption lower, and keep the cost lower. So when we go for these protocols, I2C, SPI, UART, our intention is to have the circuit simpler, reduce the power dissipation, and keep the cost lower. At what cost? Low data throughput. But we are okay with that. I mean, getting low data throughput is expected, and we are fine with that. Now, when we go to other application, other spectrum of the application where you want high data throughput, that is where you go for high-speed protocols. Basically, high-speed protocols requires a special analog circuitry which receives and transmits signals at very high speeds. Okay, this analog circuitry requires clock generation, clock recovery, serialization, and deserialization logic, which is essentially what we are calling as the phi. So one of the distinguishing factors, if you ask what is the one of the distinguishing factors between high speed and low speed protocols, phi is the one of the unique things that differentiates, that makes high speed protocols possible. So what is that phi essentially has? Phi has the circuitry for clock generation, clock recovery, serialization, and deserialization. I mean, when I say clock generation, the locking the phase and given a reference clock, generating a phase locked clock, all those aspects is what I'm calling as clock generation here. Okay. So phi is the differentiating factor between, if you ask what is the essentially difference between a high speed protocol and a low speed protocol. So phi is the differentiating factor. So phi enables the data transfers to happen in the range of gigabytes per second. Whereas in low speed protocols, it will be megabytes per second, right? In some cases, it could be as low as kilobytes per second. But when you want to target the speeds, you need a special circuitry which does all these aspects: clock generation, recovery, serialization, deserialization, all those aspects. That circuit is called as phi. So due to this, it results in high data throughput. But since you are introducing this complex circuitry and you need high data transfers and you need to implement a lot of features for this requirement, the circuit complexity increases and it essentially results in more power dissipation and it comes at a higher cost. Okay, so this is the cost you are paying for achieving high data throughput. So what are the examples of high-speed protocols? USB 2.0, USB 3.0, USB 4, PCI Express, SATA, DDR. These are all the examples of high-speed protocols. Next. In the previous session, we have talked about USB Implementers Forum. So it's a group of companies. It's a consortium of companies. You probably, if you open the spec, you will find that there are almost 50 to 100 companies which make that consortium, and they target may not be 50 to 100, less than 50, of course. This consortium of companies probably meet once in a year or sometimes, and they come up with the revised specs, or they keep uh, uh, brainstorming about how the next generation of USB can be implemented. So their target remains simple. USB Implementers Forum targets at implementing a protocol which provides following aspects. Their goal is simple. They want to get better performance out of the protocol, and it should be achieved with low power consumption, it should have proper error handling mechanism, and it should have proper interrupt handling mechanism, and it should all be done at as low cost as possible. I mean, there is a cost for everything, but how can we still reduce that cost? And it should be portable, and it should be hot plug compliant. I mean, hot plug means you should just be able to insert the device and you should use it without switching off and switching on the device again. And it should be backward compatible. So when we say backward compatible, even though our device is USB 4, but my laptop host is USB 3 based drivers, it should still be able to support my device and vice versa. So that concept is what we call as backward compatible. So in summary, the focus of USB Implementers Forum is to achieve all these aspects: better performance, low power, proper error handling, and proper interrupt handling, achieving low cost, and keeping it portable and hot plug, and keeping it backward compatible. Now, since we are talking about this, when the USB 4 spec was released, so essentially what it indicates, I mean, what is the summary of USB 4 is, USB 4 by itself doesn't provide any generic data transfer mechanism or device classes like USB 3.x. I mean, it relies on USB 4 implementation, completely relies on 3.x implementation. It doesn't add any new data transfer mechanism. It doesn't add any device classes. So whatever that is there in USB 3.x, it very much applies to USB 4. So then if that is the case, what is that USB 4 essentially does? USB 4 serves mostly as a way to tunnel other protocols. See, USB 4 is kind of developed on top of USB 3, including everything of USB 3, and it is meant to tunnel. What is meant by tunneling? We'll discuss here. Tunnel the protocols like USB 3.2, which is the just one generation before USB 3, USB 4. Tunnel DisplayPort, it is another kind of protocol, and optionally the PCI Express. It also supports host-to-host tunnel. Let's say you're connected one host, you're connected another host, you're connecting. So it supports this communication between host to host as well. What is tunneling? Just a very quick definition. Tunneling is basically a way to move packets from one network to another. In this case, when we say one network, we are talking about USB kind of protocol network to display port kind of device. Let's say on one network, you're working with USB 3.0 hardware. On the other side, you have display port. You want to send this kind of packets. How do you send that? The concept that you use is tunneling. By basically, how do we achieve this concept? It is done by the means of packet encapsulation. What is packet encapsulation here? Wrapping a packet inside another packet. So you are going to wrap a display port packet inside PCI Express, inside USB packet. You are going to wrap PCI Express packet inside USB packet. Essentially, the end device knows that I am going to get display port packet only, but it is coming with a wrap of USB packet. So this concept is what we call as tunneling. As we go forward, we'll understand how tunneling actually gets implemented. For today's session, it's not much relevant. Okay. So how does USB address above requirements? So we have discussed that we want better performance, low power consumption, proper error handling, interrupt handling, low cost, portable, backward compatible. So how does USB do that? So basically, USB implements various features in different layers. It achieves all this by implementing various features in various layers, in different layers, to achieve various requirements. Like, I mean, I don't want to read again all those things. You understand, right? Basically, the USB protocol implements features into different layers. Like you can say more in line with OSI reference model. See, the OSI reference model divides the whole communication between one device to other device into 7 layers, right? You would be aware: application layer, network layer, session layer, transport layer, link layer, physical layer. There are almost 7 layers. It uses those concepts. And it implements features into different layers. So when we say USB 3.2 or anything 3.x, it has got protocol layer, it has got link layer, It has got physical layer. So not everything is implemented into protocol layer, not everything is implemented into link layer. Based on what is it supposed to do, different features are implemented into different layers. So the protocol layer is meant for generating the packets, generating the transactions, or generating the packets, different types of packets. And there are 4 types of packets. As we go forward, we'll discuss. And the link layer is responsible for link integrity checks, flow control mechanism, and power management. Physical layer is responsible for handling the lower level of link, lower level aspects of the link. It could be encoding that we discussed, right? 8-bit NB encoding, 128B by 132B encoding, clock recovery, serialization, deserialization. So all those aspects. And it has got a concept called, okay, sorry, here only it gets implemented. LTSSM, through which we achieve various miscellaneous aspects like low power capabilities. Then we achieve the concept of recovery, error recovery, recovery from the error, or we can call as error handling. And then configuring the link. I mean, configuring the link or link parameters. So essentially, you see, the whole functionality is divided across various layers. One we call as protocol layer, one we call as link layer, one is physical layer. So protocol layer is responsible for generating the packets and acknowledging the incoming packets. I mean, handling the incoming packets, of course, packets, and forwarding it to the next layers, further next layers, next connected devices. I would not say layers because that would be a wrong thing. Connected devices. Then link layer, which is responsible for link integrity checks, making sure that the packets are going properly from one device to one port to another port. Then flow control, making sure that we have enough buffer space on the other side so that we are sending only if the buffer space is available. If the other port doesn't have enough space, I'm not going to send any packet. So that mechanism is called as flow control. Then it also does power management. What is meant by power management is, as you know, most of the USB applications are portable applications, right? I mean, the power holds a very significant impact in USB applications. So reducing the power has, is a significant part of USB functionality. So USB introduces some states called as U1, U2, U3. It introduces states called as U1, U2, U3, which gives various levels of power saving. So, and all these concepts are implemented through the means of LTSSM. Then we have physical layer, which handles the very low level aspects of the link, encoding, clock recovery, deserialization, serialization, all those aspects it handles. And primarily, USB is a host-centric protocol. What is meant by host-centric protocol? If you take USB topology, it consists of many components: host, the link, the device, or we can call as interconnect, and device or hub also. Hub is also a type of device only. It is counted among a type of device only. Among all the things which are involved in the USB topology, it is the host is the only one which tells what should happen at any point of time. I mean, why do we call USB as a host-centric protocol? Why USB is called host-centric protocol? Because everything at any point of time is completely decided by or scheduled. I would say scheduled decided is not a right word, scheduled by the host. I mean, when to initiate communication to specific device. Okay, when to send a packet, all those aspects, unless there is something device intervention is required. Let's say device can say, I am not ready. I have got into an error condition. That is where device will come into picture. But the communication gets initiated with host. So see, of course, device has right. Device, I will call not device, I'll call it as function, has right to say, I am busy or I got into error. That is fine. But even for even for this to happen, it is the host which most of the times initiate that communication, which most of the times initiates that whole transaction. Hence, it is called as host-centric protocol. Now, how does host work? How does host know what to do at any point of time? How does it figure out which device is there, to which device to send a packet to? Everything we will talk as we go forward in the session. By now, you should have got a clarity. What do we mean by host-centric protocol? In very simple terms, our laptop is like a host. When you connect a pen drive, laptop is like a host. Our pen drive is like the device, is the function. The cable which is connecting both of them is like the interconnect. In this case, there is no hub because we are only connecting one pen drive to a laptop. There is no hub comes into picture. In this whole case, it is the laptop which controls everything, all the transactions to pen drive. When to write into the pen drive, when to read from the pen drive, everything is decided by the laptop only. Hence, we call it as host-centric protocol. Every generation of USB has improved version of 5, which enables them to transfer at higher rates compared to earlier generations. See, if you ask me what is the major thing that is differing between one generation to other generation, it is 5 which makes the biggest difference. Because of that, we are achieving higher data rates from one generation to what is a USB hub. See, USB hub, this is a question one of the participants has asked. So USB hub has one upstream port and multiple downstream ports. A USB component, USB topology component, which has, I mean, this is the technical definition. You ask me technical definition. In a more generic terms, if you, I mean, the USB topology supports connecting up to 127 devices. Like you can connect a pen drive. This is my laptop. I can connect a pen drive here. Okay.
Sir, one doubt here.
Yeah.
In the USB topology component, one upstream. Here I have understand upstream means device, and the downstream means host. So if we are connecting,
See, what I'm telling is, upstream and downstream should not be confused with host and devices. I will explain. First, let me answer this. Then I will answer your question. Okay. I will complete this explanation. So USB topology supports up to connecting 127 devices. In this case, we have only connected one device. What if I want to connect 10 pen drives? Will you have 10 USB ports here? 10 USB connectors won't be there, right? In my laptop. So what I do is I use the concept called as hub. Hub will have multiple ports like this. Here I can connect one pen drive. Here I can connect one pen drive. Here I can connect one pen drive. If I want, I can connect one more hub here. I can then connect some more pen drive. The concept of upstream and downstream is very simple, not to be confused. Upstream means anything that is facing the host is upstream. Any port that is facing towards host is upstream port. Any port that is facing away from the host is downstream port. So in this case, let me ask you, what is this port? Sorry, what is this port? This is a downstream port. What is this? This is the host. This host. These are all the devices or functions. This is hub. This is hub. This is device. This is device. Device. So for better understanding, I'll write H. Device. Hub. Hub. Rest are all devices. D, 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 D. Now tell me, what is this? Is it upstream port or downstream port?
Upstream.
Upstream port. What about this?
Downstream.
Downstream. This is also downstream.
Downstream.
This is also downstream. This is also downstream. So basically, every downstream port connects to an upstream port. So hence, every USB connection is called as a port-to-port connection. So every USB connection is called as is a end-to-end connection. Is a end-to-end connection. I would rather call device-to-device connection. More technically, we can call host-to-device connection, because host is also one kind of device only, actually speaking. Okay. This end-to-end connection consists of multiple port-to-port connections. One port-to-port connection consists of one downstream port connected to one upstream port. Please ask me your question now.
Sir, here we have understood like upstream port is like a device only, right? And the downstream port is acts like a host.
Upstream port.
See, when the data transfer
always,
is from
device always
yeah.
No, the device only has upstream ports only.
Yeah.
Root host only has downstream ports only. Hub is a mix of upstream and downstream. Is it clear?
Correct. Okay.
Next. So let me do one thing. I'll keep this empty. Again, drawing everything many times consumes a lot of time. Okay, so I have already told you, you get improvement through the means of the phi being improved from one generation to other generation. Phi also uses advanced encoding techniques like 64 by 66B encoding, 128B by 132B encoding. We will have one session where we will dedicatedly talk about USB phi as well. Now let us start with learning the USB protocol. So far we have just got a basics of what is USB, the basics of protocols. Then we talked about how USB supports all these aspects in terms of implementing everything in various layers: protocol layer, link layer, and physical layer. So now we'll start with learning the core aspects of USB protocol. So to learn USB 4, we need to learn USB 3. To learn USB 3, we need to learn USB 2. If you ask me, do I need to learn 1.0 also? Not required, because 3.0, 2.0 and 1.0 have a lot of things in common. So we don't need to start at 1.0 level. You can directly start with USB 2.0. Now, if you ask me a question, is it possible to learn USB 3.0 or 4.0 without knowing USB 2.0 completely altogether without knowing? It will be very difficult, because almost all the aspects of 2.0 apply to 3.x also. I would not say almost all, majority of the aspects, in terms of the concept of endpoints, in terms of the topology, in terms of the endpoint type supported, in terms of the packet sizes, in terms of the how the data transfer communication happens between host, hub, and devices. So a lot of those concepts are taken from 2.0 into 3.x. And as I told you, USB 4 itself doesn't have any major protocol additions. It doesn't add any new device classes, or it doesn't add any new packet types or new transfer types. It is all the common concepts. Hence, we will be spending some time learning USB 2.0, a significant part of time learning USB 3.x, and some time learning USB 4 as well. So right now we will start with USB 2.0.
Srinivas?
Yeah.
So I have some questions on the basics actually. So before going into the protocol, so you mentioned like the transfer speeds for different versions, no?
Yeah.
So, and you also mentioned like even USB 4, which is having super speed plus, will support the high speed and full speed.
Yes.
So will there be a programming control like what should be the transfer speed, or it is a hardware?
It is the speed is hardwired. See, okay. First question is the data rate of USB specific generation. Is it fixed to the generation specified speed? That is first question. What are the components inside the hub? This is another question. Okay. So yes, this will be data rate is fixed. Okay, if it is meant to work at 5 gigabits per second, 10 gigabits per second, or 20 gigabits per second, or for that matter 40 gigabits per second, it's fixed. But many times what happens is, if there is nothing to transfer, USB link will either enter into low power state. That could be U1, U2, U3, based on how the upper layers are indicating to what state to move to. Or the USB will transmit idle symbols. Idle symbols does not add to the actual bandwidth. See, but overall, however, when transfers do happen, they will happen at scheduled data rate only. Is it clear?
Srinivas, one continuation question for this actually. Yeah. So if data rate is fixed, how USB is backward compatible?
No, it has got the additional logic. Basically, if you say USB 3, the next question is what? How, if data rate is fixed, how USB is backward compatible? Okay. Basically, if you take USB 3.x architecture topology, it is actually USB 3.x topology plus USB 2.0 topology. So when I say topology, I would not say topology, connections I will say. Okay. What does it mean is a USB 3.x wire link or the wire will have both super speed wires plus high speed wires. A USB 3.x hub will have super speed hub plus high speed hub also. I mean high speed, or I would not say high speed, I will say high speed or full speed, because I should still be supporting full speed also, right? I would say USB, rather I will call it as USB 2.0 wires. Okay. Now USB device don't have that thing, right? See, for device there is no such thing. USB device is either USB 3.x based or USB 2.0 based. USB 2.0 based. So this additional, and even USB host also has super speed related drivers, related controller and drivers, plus USB 2.0 related controller and drivers. Because of this, the same USB 3.x connection will be able to work at USB 2.0 because the interconnects have the USB 2.0 wires. The hubs have high speed and full speed hub. When someone manufactures USB hub, they don't just manufacture super speed compatible one, they also manufacture USB 2.0 compatible hub in it. You can say, you can actually divide, let's say this is hub, you can divide it into two parts: super speed hub, USB 2.0 hub. So if you want to do 2.0 communication, this part of the logic gets used. If you want to do the super speed communication, this part of the logic gets used. But at same time, you won't be able to do both. I hope it answers your question.
Yes, Srinivas. So the pins in 2.0 will be same like the pins in 3.0. I mean, it's generally like how many pins will be there, and it should be in increasing order only, right? It shouldn't be decreasing.
Yes. Basically, the USB 2.0 requires pins in different USB connections. USB 2.0 requires 4 pins, as you know. One is B plus, one is B minus, one is B plus, and one is ground. Okay. USB super speed 3.x will have additionally 8 pins. One is super speed transmit plus, super speed transmit minus, super speed receive plus, super speed receive minus. I think it will also have the voltage source V plus and ground, which will add up to 8 wires. 6 wires. There is 2 more. I will just confirm you in some time. I think 6 only. Yeah. Let me not make a statement. I will confirm in some time this part. Okay. But this will be there. Super speed. So these two are different. If you are doing a high speed transfers, these 2 wires are used. If you are doing any super speed transfer, these wires are used. When I said link or wire, all these pins will be there.
Yes, Srinivas, it is clear. So next question is on the USB acting as a host. So it will be only in the case of data transfers, right? I mean, without processor intervention. Is my understanding correct?
USB always has a concept of host. See, without host, there is no concept of USB topology.
Okay, USB, so topology wise, we will be having host device, those things you mentioned.
Compulsory requires host. See, processor in turn communicates with USB host. That how it does, it's something, it's architecture specific, right? It might do through AXI or HB or any other on-chip protocol, but host is compulsory. I'm not sure if I
Yes,
understood your question correctly.
Yes, Srinivas. Yes,
You
clear.
need to isolate processor and host completely.
Correct,
Next.
got it.
What is the... Please do.
You mentioned like without changing data transfer mechanism in USB 4 compared to USB 3.
Yes.
So can we expect like changes only in the 5, which is doubling the data
No,
rate?
not like that. No. The changes are there, right? Changes are there. I mean, now the next question is, what are the changes? Now, why, if no new data transfers or no new, what is the data transfers and something else we discussed, and transfer types or the features. No new data transfers are added in USB 4.0. In USB 4, there's nothing like 4.0. It's USB 4. Is the changes only in 5? No, because majorly USB 4 supports tunneling, supports various other protocol tunneling, other technologies tunneling. Okay, so this tunneling has to be initiated at the upper layers only, right? The 5 is not responsible for framing the packets. I mean, for creating the packets or encapsulating the packet. It is the upper layer's responsibility. That means there is a layer called as configuration layer. There is a layer called as adapter layer, which essentially play the role of a protocol layer. There we generate all these things. So there is a change happened here also. There will be some changes in transport layer also. There will be changes in file layer also. But majorly whatever concepts we discuss for USB 3.x in terms of how the transfers will happen, how the endpoints are handled, how the error handling happens, how the power management happens, many of those concepts will be applicable to USB 4. But if you ask me, is the change only into 5? No, it is into other layers as
well. Okay, Srinivas. Yes, clear on this. And Srinivas, the slides will be, not the slide, notes will be shared, right? Because a lot of answers are here.
Notes will be shared. I mean, that is the very reason I make a notes. I make a notes for 2 reasons. One, I slow down when I teach. Otherwise, I will be talking and I don't realize whether I'm talking fast or slow. My intention is to talk slow, but I lose the track. So this automatically slows down my speed. Second is I give this note so that anytime, even after 1 or 2 years, you look back, you know what has been done in session 1, session 2, session 3, you have an idea. And even this presentation will be shared with you. So you will have lifetime access to this presentation. Okay. Of course, all the other course material will be shared with you, notes, assignments, and the protocol specifications, the presentation, all those aspects will be sharing with you. Now,
okay,
what are the next question is, what are the components inside the hub? See, hub is kind of a routing logic, because when a packet comes, at downstream port or upstream port, it is responsible for routing it to one of the downstream ports, right? Vice versa. So now, what do you think would be required for implementing a routing logic? Some kind of temporary buffer space, some kind of logic which does the multiplexing and demuxing, all those things, right? That is the same logic that goes into the hub.
Hi Srinivas, I have a question on hub.
Yeah,
by chance, if you're connecting USB 2 device, that enumeration can happen, correct? So
yes,
whether this hub, if a device connected on the hub and to the host, so the enumeration is handled by the host.
Yes.
Correct.
Yes.
So I think hub is the no play part in enumeration of the devices.
Hub is you are telling hub doesn't play any role in the enumeration. Is it what you are telling?
Yes, that's my question.
Yes, I mean, see, if the device is coming into picture, hub doesn't play any role, but see, it is the hub which is supposed to route the packet, right, towards the device. isn't it?
Okay.
So hub has the role to play in terms of routing the packets which are coming from host to device and device to host.
Okay, but how it will understand that whether the connected device would be the USB 2 or USB 3? How the how the hub will recognize whether this is a
The
USB 2
hub will
device or
recognize
USB 3
through
device?
electrical mechanism.
Okay.
See, we will talk about all those aspects in the coming slides. I mean, how the host will figure out whether a full speed, low speed device is connected or full speed device is connected. All those aspects we'll talk.
Sure. Sure.
I mean, today's session itself will have some of those aspects covered, and later when we move to the next slide, tomorrow's session, we'll talk about how my host recognizes the other devices as well.
Sure.
So we will start our learning with these aspects. Can you please read this list once? So we will start USB 2.0 with learning the protocol basics. Then we'll discuss about USB 2.0 topology. Then how host device communication happens. What is the concept of endpoints? What is frame, microframe? How the error handling happens? How the interrupt handling happens? And power management in USB 2.0. So let us start with the USB 2.0 protocol basics. USB 2.0 supports 3 speeds. It supports low speed, which is 1.5 megabits per second, full speed, which is 12 megabits per second, high speed 480 megabits per second. See, in this one thing we need to remember is when we say USB is working at 480 megabits per second, it is the link data rate, not the effective data transfer. I mean, our whatever packet, let's say I need to send 1 megabyte of data. So there will be lot of overhead. There will be lot of overhead added due to other packets being involved and other framing that is involved. So the point I want to tell here is, do not assume that 480 Mbps is the effective data rate. No, it won't be effective data rate. It is the rate at which link transfers will happen, but effective data rate will be even lesser because there will be a overhead added due to other packets. And framing being involved. We do some framing so that we can easily recognize what packet is coming, when the packet is ending, everything. For that purpose, there will be some overhead that reduces the effective data transfer. USB 2.0 has following features: device detection. I mean, if you look from a verification engineer perspective, let's say you are verifying USB 2.0 device, core or anything, first these are the features we have to talk about: device detection, speed negotiation, enumeration, data transfers, suspend and resume signaling, error handling, and interrupt handling. These are the features we need to talk about. So we will also be focusing on all these aspects in the today's session. Now let's start with understanding the USB 2.0 topology. USB 2.0 is basically a star topology. why it is star topology? If you see this, it looks more like a star, right? I mean, this kind of resembles the star kind of things, hence they call it as star topology. One host connected to multiple devices through hubs. So this is a hub. This is a hub. Wherever you see one upstream port and multiple downstream port, that is essentially a hub. This is a hub. This is a hub. This is a hub. Okay. And as a protocol, it supports up to 127 devices per controller maximum. I mean, if you add up all these numbers, including the hub, 1, 2, 3, 4, 5, 6, it can maximum go to 127. Beyond 127, it is not possible because that is a limitation of USB 2.0. Even talking from a practical user's perspective, you never want to connect 127 devices to one laptop, right? Can we imagine a laptop being connected with 127 pen drives or 127 types of USB devices? No, right? Theoretically, it is the maximum possible. In real life, seldom we use 127. We hardly work 3-4 kind of devices. Now, where does this number 127 limitation come from? Everything we'll discuss as we go forward in the protocol. Further to the topology, yeah.
Here the controller 127 devices per controller means controller is the RTL, right? My understanding.
Controller is part of the RTL, but one RTL can have multiple controllers. So if you have multiple controllers, that means you can connect those many multiples of devices. Okay. But your question is controller part of the RTL? Yes, it is part of the RTL. See, for that matter, everything is RTL. Your question rather should be, is it part of the host? Yes, it is the host.
Correct. Okay. Understood.
Okay. So next, continuation to 2.0 topology, full speed and high speeds hubs extend USB 2.0 topology. The point is what? If you want to connect more devices, you use hubs to extend the topology. Low speed does not support hubs. Low speed devices don't have concept of hubs. Hubs also help detect device attach and removal. I mean, hubs have some kind of electrical circuitry. When you connect, a circuit gets closed through which they figure out a device has been attached, device has been removed. That information they pass on to the host. Supply port power, and what else hubs do? Hubs supply port power and forward the traffic. When a traffic comes from host, it sends it to the devices. When the traffic comes from the device, it sends it to the host. And as a limitation, you can connect only 5 hubs in a series. You cannot have more hierarchies in hubs. For example, this is 0-1 hierarchy, this is 2nd hierarchy, this is 3rd hierarchy, 4th hierarchy, 5th hierarchy. Now you cannot have any more hubs here because you can have maximum 5 hubs in the series. Now here you have to connect only the devices. It is not possible to connect any hubs beyond this.
Hello.
Yeah.
So what does that actually hub? What does it contains?
What does
that hub? Is that a connectivity between devices and controller? What hub means? What?
Hub means it's like a switch. In a very basic terminology, it's like a switch. You want to connect. See, there is only one physical port here. You cannot connect 2 pen drives. Is it possible to insert 2 pen drives 3 pen drives into the same port on your laptop?
No.
Not possible, right? So in that case, what option they give is you can purchase a hub from the market. Okay, where it will come with 3 USB ports or 4 USB ports based on what is the hub is about. Then you can connect device here, pen drive here. You can connect a pen drive here. You can connect a pen drive here. When the traffic comes from here, I mean, in USB 2.0, it actually broadcasts. When the traffic comes from the device, it sends it to host. Hub is something that is connecting one side of the port which is connected to the host with on the other side connected to the devices.
Okay, more or like switch.
Yeah, more like a switch only. Yes.
And it is like a bridge also between host.
Hub is not exactly a switch. See, hub has a functionality similar to switch. Works somewhat similar to switch, but not exactly switch. Why? What is the difference? Switch has a fixed port to which it is going to send the traffic, send the packet. Whereas hub broadcasts the traffic, the packet to all devices, to all the devices. At least in case of USB till USB 2.0. In USB
Hello,
3.0
sir.
it will change. So hence hub and switch are not same. But in summary, they are connecting host to other devices or multiple devices. Is it clear?
Hello, sir. Hello.
Yeah, please tell me.
There is any maximum chance to connect to the hub? Only 3 switches or more than that we can use?
No. See, you can properly connect more devices also. More
Okay.
devices also. Technically, I'm not sure what is the limitation a hub can have, but you can have this limitation is there. One hub, next second hub, third level, fourth level, fifth level. Beyond this, you cannot have hubs. It has to be device only. I think technically you can have any number of devices as long as the hub supports. I believe you can have any number of downstream ports.
Okay.
This hub,
Srinivas, here I want to add one thing. Hub is
Yeah.
like a device, one of the device. Without a hub, only we needed 2 ports. One port is for the device and one port for the host. If I
Yes.
wanted to connect different devices, I need to use the hub in order to increase the ports.
Of course. Yeah, that's probably the right way to put what is hub.
Yeah, in order to increase the ports, in the sense we need to increase the connection of the more number of devices. We'll use the hub. Hub is like a device.
Yes, hub is also a category of device.
Kind of device. Yeah.
Hello. Hello.
Yeah, please
Srinivas,
tell me.
I have a question here. So,
Yeah.
is there a possibility where one device can communicate with other device without host intervention? Like,
No,
there
it's
are
not
like,
possible. It is not possible.
okay.
In PCI Express, it's possible, but in USB, it's not possible.
So, if there's a case like we have an audio file in a pen drive, and if we want to hear it from a USB speaker,
Yeah.
in that case, that file should go into host memory, and then from host memory, it should come back to the speaker.
Yes, very much. That is the how it has to work, because it is host centric. The host has to be involved in every communication. See, how I would put your question is, any communication that happens, it has to be host initiated communication, and host has to get that data. And so in your case where you have to do from device to device, host memory has to come into picture.
Okay. And one more question I have is, in the previous slide, you have said host doesn't support low speed.
Hub doesn't speed. I mean, low
Sorry.
speed protocol doesn't have hub. Low speed is 1.0, right? I mean, there probably back then we didn't had so much bandwidth requirement. Anyway, please ask your question.
Yeah. Sorry. Low speed 2.0 has low speed, high speed, and then full speed, right?
Yes.
So, like if I have a USB 2 device, 2.0 device, which has low speed compatibility, and if I want to plug it in the hub, does it support that, or?
It doesn't support, right? Because the hub itself doesn't support low speed, right?
Okay. So
The
if we
low speed
design,
itself doesn't have a I mean, then in that case, it has to be directly connected to host itself.
Okay.
Okay. One more question is data transfer rate changes if you use 5th level of hub. So it doesn't change. Data transfer rate will be effectively same only. I think these questions you will understand as we discuss forward. I mean, as we understand the whole concept of USB frame, micro frame, it will be more effective. You'll understand easily. How host differentiate device connected is whether hub or USB 2.0. there is a concept of descriptors. Each device, each hub and device through which host knows what type of device is connected, what type of device is connected. So this we'll discuss when we go to enumeration. We'll talk about this concept. If a large number of devices are connected, what is the question? If large number of devices are connected, then timeout may happen. How is it handled? In this case, there is a concept called as, the USB divides all the transfers into two categories. One which require periodic transfers, one which doesn't require periodic transfers. So these are given the highest priority. These are given the lower priority, of course, as you see. Okay. So the USB host distributes the available bandwidth among these transfers as per the current application requirements. Yes, if your question is if large number of devices are connected, then timeout may happen. So the timeout will be resulted through, see, first of all, timeout will happen if large number of devices are connected. Large number of devices are connected. With large number of devices connected, it is the host which is not able to send any transfers to the device. So then there is no concept of timeout. When does timeout come? I have sent a request to device and it is not able to, I am not able to get response back in specific time. That is what I call as timeout. But in this case, with large number of devices connected, the protocol, my scheduling is such that I am not able to address one of the device. So then there is no concept of timeout. Basically, the problem is I am not able to schedule the transfers to that device itself. So that doesn't result in timeout. So if at all timeout happens, timeout is handled in a different manner by in terms of generating some kind of errors will be there. In case of when you go to USB 3.0 and super speed, there will be some kind of errors which will be generated to handle error scenarios. This timeout errors.
Watchdog timer will be implemented.
Watchdog timer won't be there inside the USB. It's a component that goes into SoC, right?
Okay.
To my knowledge, watchdog timer won't have any direct significance with USB topology. USB topology has a different concept where it measures. I have given a request and within how much time response has to come. If it doesn't come, it generates a timeout. Next. Can we control hub to communicate with only, even though it is connected to more than? It is not possible. It is the host which has to decide everything. Okay, if the question is it possible to configure the hub for this? No. Can we configure hub to only communicate with two devices? No. Rather, you don't do any transactions targeting the devices. Next, how the enumeration happens between hub and device for USB 2.0. Enumeration is between host and device. Hub is only facilitating the packet forwarding. So there is no enumeration between hub and device. It is between host and device. Now, if your question is how the enumeration happens between host and device, we will talk about that in the coming slides. I hope it is clear to you. Let's go to the next aspect. So we talked about this. We talked about this as well. So now let us understand how USB 2.0 functionality is implemented. You can imagine the USB 2.0 topology in this manner. Host has a host control interface. On the host side, there is one UTMI. It stands for USB 2.0. I have a request. Let's first make some progress with the USB 2.0 protocol. Mostly 90% of all your questions will be answered. I haven't talked about speed negotiation. I haven't talked about enumeration so far, at least for last 1 hour. So let's wait till end of the session or maybe another 1 hour. Then I'll answer all your questions. You please keep all your questions till that point. Once these things are done, if you still think that something is not been answered, then I'll address all your questions. Okay. So now let us understand how USB 2.0 functionality is implemented. So we discussed that host connected to host control interface. And on the host interface side, you have one UTM, which is essentially the PHY. This USB 2.0 transceiver macro cell. UTMI stands for USB 2.0 transceiver macro cell. Transceiver means transmitter and receiver. This is essentially we are calling as USB 2.0 PHY. And on the other side, you have the interconnect. This is USB link, which is connecting it is connecting host to device. On the device side, you have again UTMI. So basically, PHY is at both the host side and at the device side. Then you have USB 2.0 device core. Then you have function controller. This function controller is what is really our function is about. It could be printer, it could be the music player, it could be the storage device, it could be some adapter, anything. Because this is our core functionality. What is this whole topology is enabling is, if you ask me, what is this is doing for us is, it is enabling us establish a connection between host and function controller, which will help us achieve very high speed data transfers at a low power consumption with a proper error handling and proper interrupt handling abilities. At the end, USB protocol is not a sink of data nor a source of data. In summary, what is it? USB protocol by itself is not a source or not a sink of the data. It only facilitates very high speed data transfer between host and function controller with lower power consumption, with proper error handling ability and interrupt handling, all these aspects. So please remember, note that USB doesn't generate data, USB doesn't consume data. It is only the medium. Like SPI is there. For example, SPI is also a medium. SPI is also a medium for data transfer between SPI master and SPI slave. Same is with USB also. Just that USB helps us achieve high data throughputs. SPI works at a lower throughputs. USB is a host-centric protocol. So USB in general, it could be USB 1.0, 2.0, 3.x, 4.4. They are all host-centric. So that means USB 2.0 is also a host-centric protocol. PCI Express is not exactly host-centric. PCI Express is not host-centric. Even in PCI Express, even devices can initiate transfers. It is possible for one device to initiate a transaction to the host or to the other devices. Whereas in USB, it is not possible. Everything has to be initiated by the host itself. In USB 2.0, devices can be thought of as a set of endpoints. There is a concept called as endpoint. I mean, whenever you go to any high-speed protocols, right, you will come across the endpoint concept. What is endpoint, we'll discuss in the coming slides. All the data movement is between device endpoint buffers and the host memory buffers. I told you, right? USB is only facilitating the data transfer between host and function controller. In very simple terms, host has a buffer memory. It can be any kind of memory, and my function controller has associated data buffers, which we are technically called as endpoints. So USB 2.0 helps establish this connection between host memory and function controller memory. USB 2, what is UTM stands for? UTM stands for USB 2.0 transceiver macro cell, which is also called USB 2.0 5. On one side, if I imagine UTM, you may ask what is UTMI is about. UTMI is basically can be imagined like this. If this is my pen drive, okay, I would call this side as the UTM. This is the USB core functionality. This is the function controller. If this is my host, to which I'm connecting, there is a buffer here, there is a buffer here. We are essentially doing the transfer between here to here. That is what is happening. It could be either in this direction, or it could be either from device to host direction. So this is a virtual pipe. This is a virtual pipe. Virtual pipe means non-existent pipe. See, really this is the connection, but you are establishing a non-existent pipe connection. There is no real physical pipe is there, but you're establishing that connection. That is essentially what we call as the endpoint concept. That concept is what we call as the endpoint. So in summary, we can divide the whole concept into, if this is my pen drive, I can divide it into 3 parts. One side UTM, through which it connects to my USB cable. It gets the data, deserializes it, I mean converts it into parallel data, gives it to my USB core. USB core understands the data and further gives it to my function controller. It doesn't directly give it. It writes it into a buffer memory. There is a memory into which it writes, and it indicates through a DMA request. There will be a DMA request from host to not host, USB core to my function controller. So function controller knows that some data is written into buffer memory. Now it goes and performs the read from it. I will explain this aspect in the coming slides again. Okay, so if you take UTM, that is USB 2.0 transceiver macro cell, on one side it connects to D plus and D minus. D plus and D minus are used for differential signaling, so for proper noise cancellation. I mean, if there is any noise on D plus, and D minus helps cancel that noise, so hence we go with differential signaling. On the other side, it has got a parallel interface. The parallel interface can be either 8-bit or 16-bit data bus with valid and ready signals. When the data comes on D plus and D minus from the host, the UTM, that is USB 2.0 transceiver macro cell, deserializes. Deserializing means what? Parallelizes this data into either 8 or 16-bit format, which is given to USB 2.0 core. What happens when the data comes from my laptop or my host? The UTMI is responsible for understanding this D plus and D minus, and from that it will create a pattern of 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, gives those data to my USB core. Core further handles this 8-bit data patterns. This data in general, the whatever data comes from host will come as a series of startup frame, token packet, data packet, and handshake packet and special packets. So to understand this, we need to understand the concept of what is a frame, what is a micro frame. We'll discuss all those aspects in the coming slides. Okay. Now USB 2.0 devices, example USB pen drive, can be thought of as 3 elements. One side is UTM, which is one side connecting to D plus D minus, and the other side it is connecting to USB 2.0 core. And the other component is USB 2.0 core, which implements the core USB functionality. I mean, it implements the USB protocol behavior. So UTM acts as USB 2.0 one side interfaces with USB wire, USB line, that is D plus and D minus. Other side with USB 2.0 core. Basically, UTM deserializes the data coming on D plus D minus, gives this data in 8-bit or 16-bit format to USB 2.0 core. If we put together 8-bit or 16-bit data, I will not confuse you too much. I'll remove 16-bit. Let me keep it 8 bits only, because you will be thinking again, what is that divided by 16-bit data? If you put together 8-bit data patterns, they are nothing but they are a group of packets. Packets can be multiple categories: startup frame packet, token packet, data packet, handshake packet, special packet. These are the various types of packet. So the USB 2.0 core understands what type of packet is coming, and it figures out how to respond to it. I mean, through this it figures out, through above packets, the USB 2.0 core figures out whether data write is happening, means writing into pen drive, example, or data read is happening. Okay, it gives this details, write or read, to function controller. What is function controller? Example, printer is a function controller, music player, or my storage, pen drive storage, to this one. Function controller in turn either accepts the data in case of writes, provides the data in case of reads. This is the one paragraph summary of what is USB 2.0 is about. If you ask me what is USB 2.0, if you read this, this would be sufficient for you. See what is happening. Let's again understand. We have the host. We have a device. Here you have UTM. Here you have UTM. Then you have a cables, 4 cables, right? One is carrying V plus, ground, D plus, D minus. And as I said, the USB is completely host-centric protocol, means all the communication has to be initiated by the host only. Let us say this is a music player. I want to play a song in the music player by sending a data. For that purpose, what host does is it creates something called as microframe. There are two kinds of things. One is called as frame, one is called as microframe. Microframe has a specific format: SOF, token packet, data packet, handshake packet, token packet, data packet, handshake packet. Like that, series of packets will be there. You cannot send all the data at once because I have only 1-bit interface. This UTM here serializes the data. What is serializing means what? Sends this same data 1 bit at a time, 10110, like that. It sends in a bits format. It goes here. It does the reverse. It collects the 1-bit format, serial data. It deserializes the data. Whatever data comes, it deserializes and gives 8 bits at a time to the next layer. What this layer will do is, it understands what type of packet is coming. SOF, is it token packet, is it data packet, is it handshake packet, all that. Accordingly decide whether I should expect the data or I should return the data. So that whole decision making happens here. This is how this connection gets established. I mean, this is how the communication happens between host and device. So we will be talking more in depth of all these aspects in the following slides. Let us see if we need to take a break here. Yeah, I think we can take a break. Let's just read this. USB 2.0 device can be thought of as 3 parts: UTM, USB 2.0 core, and USB function controller. USB 2.0 core is further implemented using multiple endpoints. Endpoints are virtual channels. Virtual channel means non-existing channels. There is no physical channel called as multiple physical channels. It's only one line in which we are creating a virtual channel that establish the connection between host and the device. So we will talk more about these endpoints in the following slides. So let's take a break here. We will meet in 15 minutes. So when we meet, we'll continue further with the USB 2.0 functionality.
This conference will now be recorded.
So we'll resume the session now. So we were discussing about USB 2.0 functionality. So we discussed that the topology involves host on one side and function controller on the other side, which are connected through means of host controller interface, UTMI at the host, UTMI at device, USB 2.0 device core, and function controller. Then we discussed about how the UTM looks like. And then we talked about how the USB 2.0 devices are divided into UTM, USB 2.0 core, and USB function controller. Then we just got an idea of what is endpoint. Now let us discuss further. Once a device is connected to the host, but that is basically you have connected the device into USB 2.0 topology. The host has to get information about what is connected. The host needs to get information about what is connected. That process is called as enumeration. Through a means of enumeration, the host gets to know what is connected. It's not just for USB 2.0. Every high-speed protocols requires a concept of enumeration. I mean, before you do enumeration, you have to do speed negotiation. Before you do speed negotiation, there has to be device detection that has to happen. Device essentially has 2 types of register or memory spaces. You can say device has 2 types of address spaces. Device or the function has two types of address spaces. One is called as descriptors, and it's the core function memory. What is descriptors? Descriptors are the registers which are hard coded, which are populated, which are configured during device manufacturing. These descriptors tell everything about what the device is. I mean, what is the device? What type of device? How many endpoints? What type of transfer supported? All that kind of information is part of these descriptors. So the host reads all these descriptors initially. This whole process is what we call as enumeration. Basically, by reading these descriptors, host knows what type of device is connected, how many endpoints does it have, what type of transfers are supported, everything it will come to know by means of reading the descriptors. Where are the descriptors present? Descriptors are part of my pen drive. I mean my device. Descriptors are part of the device. Then you have the core function memory. See, core function memory is not involved during enumeration. This is used during functional operations. For example, playing a audio on USB audio player, on USB based music player, audio player. So the data goes into this core memory. Then audio player will play this. So that is how we divide it. Okay. Now, who does the enumeration? I mean, can someone tell me who does the enumeration? Is it done by host? Is it done by hub? Or is it done by the device?
Host. It's done by the host.
It is done by the host. Essentially, it does it through host controller and host control interface. You can divide host into again two parts: host controller, host control interface. Now, USB 2.0 host controllers, they have three categories. We don't want to get too much deep into it, but just to give you a quick overview, the USB 2.0 enhanced host control interface. EHCA stands for enhanced host control interface. This will be required when you are connecting with high-speed devices. Then there is the other category of devices: USB 1.1 UHCA, OHCA. UHCA stands for Universal Host Control Interface. OHCA stands for Open Host Control Interface. These are used for low speed and full speed device. I mean, if the device connected is a full speed device, this things comes into picture. If your device connected is a high speed device, EHCA comes into picture. Next, there can be multiple instances of host controllers to improve the concurrency and to increase the number of available ports. Basically, if I have multiple controllers in my SoC, multiple host controllers in SoC, I would be able to connect multiple instances of the pen drive devices, which would improve the concurrency and essentially increase the number of available ports as well. Can you please read this once? So enumeration is initiated by host controller. How host controller know? Yes, does multiple host controller indicate multiple hosts in the SOC? Yes, it indicates multiple hosts in the SOC. So how host controller knows when to do enumeration? That process is explained now. The whole enumeration process starts off with the device connection. So basically this is how the flow works. Device is connected. The host figures out what type of device is connected. It is through the I have a slide where I will talk about it. Whether it is full speed, whether it is low speed, full speed or super speed device, it will figure it out. But in this case, since we are talking about only 2.0, it will only figure out these aspects. Then once it is done, if it is full speed, if device is full speed, it does host and device involve a speed negotiation process where they figure out, they agree for either to work at full speed or high speed. Once it is done, now that speed is agreed, the host initiates enumeration to the device. So what happens once the device is connected? The host figures out what type of device is connected. It could be either low speed, full speed, or super speed. If the device is full speed, low speed means simple, it will only work at low speed, 1.5 megabits per second. If it is full speed, host device involve a speed negotiation process where they both talk among each other and they agree for either to working at full speed or high speed. Now that speed is agreed, it could be either full speed or high speed. Host initiates enumeration to the device. Host figures out whether low speed or full speed device is connected. Low speed device means 1.5 megabits per second, that is USB 1.0 based devices. Full speed device means USB 1.1 based on USB 2.0, sorry, 1.1 based or USB 2.0 based. Sorry, it's not on or. It can be either two things, full speed or high speed. Full speed means 12 megabits per second. Supporting device. Full speed uses frames for host to device communication. High speed uses microframes. So the full speed uses frames. Frames are 1 millisecond in duration. Microframe, high speed uses microframes. Microframes are 125 microseconds duration. Full speed communication happens at 12 megabits per second. This communication happens at 480 megabits per second. Okay. If the device is full speed, let's say if the device is full speed, then there are two possibilities. Device can either work at full speed or at high speed. If it is low speed, there is no confusion. It will only work at low speed. So since we have to decide whether to work at full speed, high speed, there is a negotiation required that is called as speed negotiation. During speed negotiation is initiated by the device. It uses some JK patterns. Speed negotiation involves some type of pattern what we call as negotiation involves transfer of some JK patterns, also called as chirp patterns between host and device. So through which they agree, either for full speed or high speed. How does it happen? I have a timing diagram, timing diagram image, which will tell whether they are agreeing for full speed or high speed. That will give more details. For normal transfers, D plus and D minus carry the same data pattern in differential manner. During speed negotiation, because during speed negotiation, normal data transfers are not happening, the D plus and D minus behavior will be different. See, during the normal transfers, both D plus and D minus have to carry the same data, right? You cannot have different data sent on D plus, D minus. But during speed negotiation, their behavior will be different. D plus, which is DP, D minus, which is DM, can either carry 00, 01, 10, 11, let's say. 00, 11 is used during normal data transfers. 00 and 11 are used during normal data transfers. During speed negotiation, we'll be using a pattern called as 01 and 10. That means on D plus, you will be sending 0 and D minus, you will be sending 1. That indicates that I am sending a K pattern. If you are sending 1 on D plus, 0 on D minus, that is called as J pattern. That is something explained here in a table mapping. Please take a look at this table.
In normal data transfer, D plus and D minus should be opposite, right? Invert of.
It's not opposite. It's not opposite. It's the same data, which is but carrying with a different polarity. See, D plus and D minus does not carry inverted data. They carry same data. With inverse noise added. I believe that is how it is done. Mean a data pattern which will cancel the noise. A pattern with a pattern, I would rather say with a pattern which would effectively cancel the noise of each other. Isn't it?
Okay, I'll check this because I assumed in reverse way. So one will be sending 0 plus noise, other will be sending voltage plus noise. So it will be a minus of
this I have taken as it is from the UTMI spec, this table. So you can see here, okay, 0 signal 0 would be 0 0. If you want to send 1 1, you would be sending 1 1. For J state, you send 0 1. For K state, you will send 1.
Okay.
But anyway, I will also check and revert on this.
Okay, thanks.
Okay. So one thing I want to tell here is, at any point, if you feel that something I have told and it doesn't logically make sense, or you know that I have told wrong, please feel free to correct me, because I always believe that there are a lot of things for me to improve, of course. So please feel free to correct me if I'm telling something wrong. Next. So now let us talk about all these aspects. Once the device is connected, what happens? The first thing is what? Device detection happens. First thing starts off is with device detection. What is involved in device detection? Please take a look at this once. Every USB 2.0 device is classified as either low speed device or full speed device. Each USB 2.0 device has 4 lines: D plus, D minus, V plus, V minus. Low speed device has a resistor connected to V plus and D minus line. You see, this is D minus line, this is D plus line, this is the device, this is the either hub or the host. In case of low speed device, you can see here low speed device, there is a resistor which is connected D minus to voltage. Whereas for full speed device, it is connected to D+. The only difference is what? In this case, it is connected here. In this case, it is connected here. Through which either the host or the hub knows whether it is full speed, whether it is low speed. That information finally is communicated to the host. What type of device is connected? Through that, we figured out what type of device is connected. Now we have to decide. If it is low speed, there is no confusion because low speed only supports low speed. Whether if it is full speed, we have to decide whether full speed or whether high speed. So that is where speed negotiation is involved. So in that case, what happens? Host figures out if full speed device supports high speed or not by means of speed negotiation. There is a mistake here. There's a mistake here. Host doesn't send. It is the device which will initiate the chirp sequence. Basically, it is the device which initiates the speed negotiation process. Once device detection is done, device initiates the speed negotiation by sending chirp K pattern. Okay, then there is a chirping sequence that happens, which is explained in this timing diagram. It's a predefined series of chirp JK pattern. Simple. Wherever you see J, you understand that they are sending this kind of pattern. D minus line with 0, D plus line with 1. Wherever you see K, you understand that D minus with 1, D plus with 0. That is how you understand it. So it is a predefined pattern of JK pattern. Like you see, for this much time, all this T3, T4, T5, T6, I mean T0, T1, T2, T3 up to T9 are very well defined. I mean the UTM spec, which is used for speed negotiation purpose, clearly tells what has to be this width, what has to be this value, what has to be this value, what has to be this value. Everything it clearly tells. So through that, there is a predefined. What is meant by predefined? This kind of pattern. After this should happen. After this should happen. After this should happen. Everything is clearly the well-established communication pattern between host and device, which finally gives indication whether the communication is established at full speed or at high speed. So chirp sequence is nothing but a predefined pattern of J and K patterns. So there are two possibilities here. There are two possibilities in the speed negotiation. What are the two possibilities? I mean the device connection established at full speed, connection established at high speed. There are two possibilities. So if the connection is established at high speed, see, if you are doing a high speed detection handshaking timing behavior and you settle for high speed mode, let's say the connection settled for high speed mode, this is how that pattern looks like. So you got a T0 device got connected. After some time, the upstream port of the device sends a chirp K pattern, In response to that, my host figures out that I'm getting a chirp K from the device. That means it is asking me whether am I capable of. See, device is indicating to me that I want high speed to be negotiated because I am high speed capable device. If the host is also capable of high speed communication, it in turn responds with KJ pattern. Till here, it was all this communication was happening in full speed frequency. This was happening in full speed. At one point, the communication moves to high speed. This becomes high speed. Till here, it was in full speed. When the termination was in high, that is full speed mode. At this point, you are switching from full speed to high speed. You further send KJ chirp patterns. So these were sent at full speed, these were sent at high speed. So you can see here, it has switched into high speed mode here. This from here onward, this is high speed. It's sent. Then finally they agreed for high speed mode, and you start, host will send a startup frame at a high speed. So this is not to be confused much. In that case, device itself won't send chubk, right? If device itself is not capable of high speed, then it won't, there won't be, this detection process itself won't be initiated. I'm answering one of the question where what if
Hello.
only, yeah.
Yeah, my question is, what if like host is only supporting low speed and device is high speed capable, or yeah, full speed capable? In that case, initially the like we have seen the pull up on D plus, right? It will detect
Yeah.
and it will, yeah, that will detect full speed, and
Yeah.
this handshaking starts in high speed
Yes.
mode.
Yes.
In high speed mode, it initiates the chip.
Handshaking doesn't start. Handshaking doesn't start. If the host is only capable of low speed, then they will, then probably that connection itself doesn't get established.
Okay, so like device, if it is supporting full speed, it cannot communicate to a low speed. Like it is not compatible with it. Like it is.
Yes. Yes. Yes.
Okay. It should be backward compatible, right? Like if a
Backward
device is a,
compatible. I am not sure whether the backward compatibility works at 1.0 level. Till 2.0 level, I am sure it works, but 1.0 level, I am not sure whether it works.
okay.
So I can check and revert on this.
Okay.
For all the time, like switching from the one mode to other mode, it requires some time.
Switching from one mode to other mode will take some time. Is that what your question was?
Yes, yes. Like so, there is like from fast mode to high speed mode. So there
Yeah.
is a so you told like so sometime after some time it goes to the other mode, right?
Yes.
Yeah, from KJ to KJ. So like that duration, it depends on what actually.
That duration is kind of implemented by the protocol. This is given by the UTMI protocol, how the speed negotiation should happen. If you open UTMI specification, you just go to Google and get UTMI specification. That will tell what should be the T0 value, what should be the T1 value, what should be the range of this, what is the possible range for T2, everything. So this has to be followed as a rule by both host and device.
Sir, here I have one doubt. Like speed negotiation is happening between the host and the device, and the device is initiated the first to the host in order to get the which speed I want. So, for example,
Yes.
here the device chips are sending the K pattern first. It
Yes.
will be the full speed. If it is sending the chirp J, is it host mode, host speed? Is it my understanding?
No. See, it is chirp K is a way device wants to say that I want to do this device speed negotiation. If it doesn't send this at all, if device doesn't send at all, there is no, you may ask, can it send chirp J? Then it's an error condition. There is no such concept of device sending chirp J. It will only send chirp K sequence. So that is the indication to the host that we need to start the process of high speed speed negotiation. If I am capable, I will send the KJ pattern.
Okay. This is standard protocol then.
Yeah, this is a standard protocol, and you see it here. It is telling, right, downstream chirps. Downstream chirps means what? Host initiated one. This is upstream chirp. This one. So upstream first device is sending, then the downstream chirp, it is the host which is sending to the device. Eventually, as they progress, they switch to high speed.
Okay.
Okay, next. USB 2.0 speed negotiation continuation. That is for if they are settling for full speed mode. See what happens. Device has sent a chirp K. In response to that, the host did not send any KJ patterns, no downstream port chirps. If there is no downstream port chirps for this much duration, between T2, T3 to T4, nothing comes, then they settle for full speed. Then it will take time. What is settling in full speed mode is, see what is full speed mode and high speed mode essentially technically means what does full speed or high speed mode technically means the phi fixing its transmitting and receiving circuitry for the either 12 megabits per second or 480 megabits per second. So it needs to be given time. That time what we are giving is this T4 to T5 time. In the earlier case we were giving this much time. T7 to T9 time we were giving. So where the circuitry can move into high speed mode circuitry. This is how speed negotiation happens. Next, what is the enumeration? Let's understand that. The host initiates series of control transfers to the device endpoint 0 to fetch all the descriptor information. See, there are few technical terms here. Let's quickly highlight them. Control transfers, endpoint 0, and descriptors. What is control transfer is basically USB supports 4 types of transfers. One is called as control transfer, one is called as isochronous transfer, one is interrupt transfers, one is bulk transfers. Control transfer is the only transfer used for accessing the descriptors. Okay. These remaining three below are used function core memory. Like we have a pen drive, you want to access the core memory of the pen drive. So it is done through bulk. Let's say we have a music player, you want to play a song, it is done through isochronous. If you have a mouse, you want to read some click data from the mouse, that is interrupt transfer. So anything related to the core functionality, it is done through these 3 transfers. Anything that involves reading the descriptors from the device, it is done through control transfer. So that is what I mentioned here. The host initiates series of control transfers. Because you are accessing the device descriptors, it uses control transfers to device EP0 to fetch all descriptor information. Now, what is a descriptor? All USB devices have a hierarchy of descriptors, which describe to the host all the information such as what the device is, who makes it. I mean, like, is it manufactured by Sony? Is it manufactured by Samsung? Is it manufactured by Micron? Like all that information it will tell. What version of USB it supports? Okay, 2.0, 3.0, 4.0, it tells for all those things. How many ways it can be configured, the number of endpoints and their types. So by reading the descriptors, my host comes to know of all these details. Basically what the device is, who made it, what version, how many ways it can be configured, number of endpoints and their types. The whole information the host will get about the device. Those descriptors are 5 types. Basically the descriptors are 5 categories. Those are listed down here: device descriptor, configuration descriptor, interface descriptor, endpoint descriptor, and string descriptor. There are 5 types of descriptors. Okay, so we won't be going into each and every descriptor, but just understand that at the end of the day, these are the things that are present in my device, which tells everything about device. As I listed here, right? All those points it talks about. Now, if I take one example of device descriptor, what does it tell? It tells what is a USB revision number, what is the product, what is the vendor ID, who manufactured it, number of possible configurations of the device can be. This defines number of configuration descriptors. This number will tell how many such descriptors are. This in turn will tell this. This in turn will tell this. So then configuration descriptors, interface descriptors, endpoint descriptors, and string descriptors. All descriptors have a well-known pattern. I mean, the pattern inside a descriptor is fixed. It is not a random data. So the host, when it reads the descriptor, it knows how to analyze the data, how to decode the data that is coming from the descriptor. So the host gets complete descriptor information during enumeration. During enumeration, host gets the complete descriptor information. After this, it has done this enumeration. Finally, it assigns a unique 7-bit function address to the device. It assigns a 7-bit unique function address to the device. Host has a tabularized information of the whole device. Just for our visualization purpose, the host has this information. Okay, device 0 is connected. It has got endpoint 1, it has got endpoint 2, it has got endpoint 1 and 2. Endpoint 0 is control transfer, endpoint 1 is this type, endpoint 2 is this type. The memory size is this much. Like that, it made a notes about one endpoint. Second endpoint, what all devices are there, what all transfers are supported, everything it makes that kind of notes. Who? Host. Next. This is how descriptors can be understood as. Please take a look at this once.
Sir, here endpoint is like a placeholder for address.
Endpoint is not a placeholder for address. Endpoint is like a it's a virtual handle, virtual channel. I'll tell you. Endpoint is a virtual channel that is used to establish a connection between host and the device. This is technically. Let's understand in a very more basic terms. This is my host. This is my, let's say, device, for example. Device has various types of requirements. You may want to play music through the device. You may want to store some data into the device. You may want to read the descriptors from the device. To implement all these features, whatever you see in the device, what device does is it implements the concept of endpoints. Endpoint 0, endpoint 1, endpoint 2, 3, 4. Endpoint 0 is always reserved for descriptors only. These descriptors are present in my device. These descriptors is what you see here. Device descriptor, configuration descriptor, configuration descriptor. Below that you have interface descriptor. Below that you have endpoint descriptor. So to read this address, there are two things my host can do. See, let's say device has the descriptors. To read this, the host targets the endpoint 0 of the device. These requests are automatically directed to descriptor information. Because endpoint 0 is mapped to device descriptors. Now, in the same thing, endpoint 1 may be mapped for some other transfer, let's say isochronous transfer. This isochronous transfer is mapped to one part of my memory. Let's say this is my big memory I'm talking about. It may be mapped to some location, endpoint 1. So when I target endpoint 1, let's say this is endpoint 1, whatever transfers I do to endpoint 1, this I'm actually doing to this location. So in very simple terms, endpoints are nothing but a memory mappings. Endpoint is more like a memory mapping. When host targets a specific endpoint, it is actually doing transfers to the corresponding memory mapping of the endpoint. Now this memory can be two types. This memory can be two types. Used for writing purpose, used for reading purpose. Okay. Let's say, what does it mean? What is the benefit of this? Is example, I want to write data into pen drive. So my host will see which all endpoints in this device support write type of transfer. Let's say endpoint 2 and endpoint 5 are supporting this. So host will target a data packet for endpoint 2. The payload that is coming in this data packet will be stored into the corresponding mapped location of the device. The function controller will get indication. It is called as DMA request will be initiated. That will get an indication that a data write has happened to the memory corresponding to endpoint number 2, because I told we are doing writing to endpoint number 2. Now function controller will go and read this data, will go and read this data from memory location mapped to endpoint. Now you may say, see, there are two things that are happening, right? One is, this is the buffer memory. You have endpoint 2. The host is targeting data here. It is redirecting it to one part of the memory. And it is telling to the device function controller that there is a transfer happened, which in turn goes and reads the data, and it in turn gets the data. You may say, rather, why don't you directly send the data here only? You don't have to, I mean, this whole thing is avoided. The whole confusion is avoided, right? You don't need to write into buffer, and you don't need to issue DMA request, and you don't need to again go and read, and you don't need to get the data. Rather, you directly get the data from host to device itself. There are some practical issues where, if for any reason, if it is not able to proceed further, it will create a back pressure, and you won't be able to do any other transfers because it is not able to complete the first transfer. This buffer ensures that you can do multiple outstanding requests. Even though you are not able to complete this, you can write to some other endpoint. You can write to some other endpoint till current endpoint is processed. Because of that, we bring in the concept of buffer. This buffer is more like playing a role of a FIFO in real life. In FIFO, what does it do? It gives that non-blocking nature. Let this happen at its own rate, let this happen at its own rate. Both become independent. Without this buffer, if I directly do this path from here to here, if there is any blockage that is happening here, block that happened here, I can't send any other packets in this direction. Does it answer your question? What is endpoint? So endpoint is not exactly one address. It is something that has been mapped to a memory location.
Yes.
So we have talked about descriptors. See, I don't want to get too much deep into descriptors. If you can just understand what is the category of descriptors, that would be sufficient. Device descriptors, configuration descriptors, interface descriptors, and endpoint descriptors.
Srinivas, my question is, this descriptor details, is it available in 8.0?
Every spec will have a very detailed explanation about the descriptors.
Correct. So my question on hardware aspects, where is it reside? Is it in the form of register format, or is it stored in any buffer or memories?
It is in the
Because
form of registers. It is in terms of registers.
register. So host want to look read those registers and understand what kind of device it is, and that each endpoint details, like as you said that isochronous transfer need to do means which endpoint should have do that isochronous transfer, correct?
Yes,
So
yes.
those details are embedded. Those details are embedded in the descriptors. That's what you are saying, correct?
Yes, 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 yes.
Okay, fine. Thanks.
Next, let's go to the next aspect. Now we have been talking about endpoints and endpoint buffers, right? What is that endpoints? What is that buffer? Let's understand. USB 2.0 supports up to 32 endpoints per a device. Endpoints provide the software interface required to fetch USB descriptors, program device features, and access the data. Basically, through endpoints, you are able to fetch the descriptors, program the device features. Let's say you want to write something into the descriptor, you can do that, and you can also access the data. So through endpoints, you are able to do three things: fetch the descriptors, program the features, and access the data. Endpoints are basically four types: control endpoint, bulk endpoint, interrupt endpoint, and isochronous endpoint. There are four types of endpoints. Control endpoint. It is used for device enumeration. What is enumeration? Fetching the descriptor information. Get the device descriptor and set the device address. These all things are done during the device enumeration. For this purpose, endpoint 0 is compulsorily used. It acts as a bidirectional endpoint. So endpoint 0 is the only special type of endpoint which acts like a bidirectional endpoint. Endpoint 0 is a special type of endpoint which is bidirectional in nature. Every USB function must implement endpoint 0. It is compulsory. You cannot avoid that. Next is bulk endpoint. See, bulk endpoint, it is used for bulk data transfer with no data latency guarantee. What does it mean is, we can divide all USB peripheral applications into three categories. One is polling based devices, peripherals. One is isochronous devices. One is bulk devices. You can say devices are peripherals, both are same. Okay, there is no difference here. Polling based peripherals. Can someone tell me what are the devices which are polling based? What do you think in USB topology, which would be? It is mouse and keyboard, for example. In this case, what happens when I enter some key on USB based keyboard? This ASCII data needs to be given to host, but USB is host centric. Host centric means what? My device can't initiate it. Device can't initiate this ASCII data transfer to host. So what? So it waits. Who is it? Device waits for interrupt type of transaction to be initiated to it, to one of its endpoint, one of its interrupt based endpoint, interrupt supported and interrupt based endpoint. So whenever it gets interrupt request, the device will say, I have data available. What is the data? ASCII data that was entered. ASCII data entered by the user on keyboard. And it sends data packet with ASCII data to the host. That is why it is called as polling based. I mean, my host is polling devices if they have any data. Essentially, it is host is polling. Essentially, host is polling all interrupt based endpoints. Not, it is not actually polling the devices. It is actually polling all interrupt based endpoints. It is asking them. Do you have any data? Do you want to do any connection with me? Do you want to do any data transfer? Asking them. Who is asking them? Interrupt based endpoints. Do you want to do any transfer? Do you want to do any data transfer with me? Okay. So do you think, can it be periodic? Do you think it has to be periodic transfer or non-periodic? I mean random, I mean on need basis. What type do you think? Interrupt will be interrupt or polling based peripheral has to be periodic transfer or non-periodic transfer?
Random transfer?
No, it has to be periodic transfer because my host has to poll an interrupt based endpoint in my keyboard at every regular interval. I mean, it could be once every 10 microseconds. Just an example, no, 10 microseconds is too small. Probably once every 10 milliseconds. So to this request, device endpoint will respond. Since we are polling at every regular 10 millisecond interval, it becomes a periodic transfer. Interrupt based endpoints are basically falls under periodic transfer category. Is it clear? Why is it periodic transfer?
Yes, Srinivas. Yes.
Okay. Yes. Okay. Next question is, if we have too many interrupts, of course, yes. Probably the host will reduce the frequency of polling. We have too many interrupt endpoints is connected to USB device. Does it load host with lot many poll services? Yes, of course. But accordingly, to offset that, probably it might reduce the number of it might reduce the frequency of polling as well. But if you consider, if you see, there is no priority based, it keeps polling. It is a schedule based and it keeps polling. More importantly, the polling interrupt transfer initialization does not consume much of bandwidth. It is just a token packet. It is just a token packet sent to the endpoint. Token packet is hardly 3 bytes. Now, even if you are targeting, let's say, even if we assume 1000 endpoints are there, we are talking about 3000 bytes of data, which is very small part of the whole frame. Okay, 1000 endpoints won't be there, right? Let's say 100 endpoints, realistically. 300 bytes, which is a very small part of whole frame. So it still doesn't put any, it still does not put any, does not take out significant bandwidth of host. I hope it is clear. This is the polling based peripherals. Next, we are talking what is the context in which we are talking this? We are discussing that all USB peripheral applications. You take anything. Let's say I randomly give you one device. It has to be either polling based, it has to be either isochronous based, it has to be either bulk based. There are only 3 categories. You cannot have any other categorization of the device. It has to be either interrupt based device, it has to be either isochronous based endpoint, it has to be either bulk based. So one more thing I want to tell is I won't say device, I will talk more from an endpoint perspective, because technically it is possible for same device to have multiple endpoints of different transfer types. So it is possible for same device to have different endpoints of different transfer types. Hence, technically we can't say device is interrupt based or isochronous based. We should rather refer from a endpoint perspective. See, endpoint is isochronous based, endpoint is interrupt based, endpoint is bulk transfer based. That is because you can have mix of endpoints. Same device can have a mix of endpoints, one supporting isochronous, one supporting interrupt, one supporting bulk. Next, that is about this. Next, let's understand what is isochronous. I think my slide will have it. Okay, isochronous endpoints are used for devices which require guaranteed data latency. Isochronous endpoints are used for what? Used for devices which require guaranteed data latency. Something like audio player. In audio player, you need to play the audio every second, right? So that means the audio player requires the continuous stream of data to be given. In those cases, we go for isochronous endpoints. Host accesses endpoints at predetermined intervals. Predetermined intervals means periodic intervals, and ensures that there is a guaranteed data transfer is happening to the audio player. In isochronous endpoint, there is no handshake packet. Handshake packet means, let's say you are listening to a song. At one point, you see some glitch happened. Will you go back and play that 1 second glitch again? No, right? You will decide to ignore that. That is how you use audio players, right? Because of that, even if the data that is sent from host to device or device to host got corrupted or got dropped for whatever reason, you decide to ignore that issues. Hence, you don't need handshake packets in case of isochronous endpoints. So in summary, we have discussed the endpoints into 3 categories: bulk endpoint, interrupt endpoint, isochronous endpoints. So far we discussed about interrupt endpoint, we discussed about isochronous endpoint. So interrupt endpoints are used for old devices accessed by host at guaranteed service intervals. Examples are like mouse and keyboard. We discussed about isochronous endpoint. Then what is bulk endpoints? Anything that is not, basically what is bulk? Any endpoint that is not isochronous requirement or interrupt requirement, and of course control transfer requirement, that is endpoint 0. That endpoint is bulk endpoint. Basically bulk endpoints are the lowest priority transfer endpoints. I mean, only if bandwidth is available, these transfers happen. Example is a printer. See, sometimes you in a laptop, we issue a print, we give a print. Okay, print happens after 5 minutes. For whatever reason. But one of the reason could be because USB host decided to keep it on low priority. Because it had many other high priority transfers. What is high priority transfers? Anything that is isochronous or interrupt becomes high priority. After all this bandwidth is done, if there is any bandwidth available, we go with bulk transfers. In summary, what does it come out of all this is the endpoints can be categorized into two categories. One is periodic transfer, one is non-periodic. What are the periodic? Can someone tell me? What are the endpoint categories, transfer types which are for periodic?
Interrupt, isochronous.
Interrupt and isochronous.
Control endpoint also comes under this category.
Control is non-periodic. What does it mean is control is done as and when the bandwidth is available. Control and bulk. Let's say I will give you an example. Where control is non-periodic. Let's say an audio player is connected. Host. We are playing audio, playing a song. Okay. Now we connect one more device. It can be anything. Example, mouse, printer, etc. Anything. So the host will do enumeration to this new device only when it gets the bandwidth. And control transfer is not a periodic transfer, right? Control transfer is one-time transfer, is one time only. Is not to be done in continuous manner. Now tell me, do you think is it periodic or non-periodic?
Yes, matching non-periodic.
Non-periodic, yeah. So we have discussed all these things. So what is bulk endpoint? It is used for bulk data transfer with no data latency guarantee. I mean, there is no committed guarantee that the data will surely come in this much time. It can be delayed. And the handshake packet is used to verify correct data delivery. But the good thing about bulk is if there is any corruption happened, there is a handshake packet comes which will tell that the corruption has happened. In isochronous, we don't have that guarantee. The example of bulk endpoints are storage devices and printers. These are the examples of bulk endpoints. So three things. There are three types of devices: endpoints, isochronous, bulk, and interrupt. Interrupt we know what is isochronous. So anything that is not interrupt, anything that is not isochronous is a bulk endpoint. I mean, technically, if you want to understand, if you want to visualize, you let's say you just did this USB demo session. Tomorrow you start looking at USB devices and you start seeing, is it isochronous, is it bulk, or is it interrupt? So this is the answer what you need to follow. How this further to whatever we discussed, how the host and device communication happens. Okay, initially user, yeah.
Srinivas, I have a question on control endpoint. So
Yeah.
you have shared like this is doing fetching the descriptor as well, setting a device address.
Yes.
Correct. Okay. The device address means what is really meaning that device address, because only one device having those endpoints. So device address
Yes.
means if it is multiple device only, then we have a multiple address. That is
Yes.
stands for. What
Yes.
really it means?
What it really means is, if you go back to one of my presentation. Okay, in this diagram, what host does is it assigns one unique address to each of them. 1 device address, 2 device address, 3 device address, 4 device address, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now each device has some endpoints: endpoint 0, endpoint 1, endpoint 2, and endpoint 3. Let's say endpoint 1 is for isochronous transfer, isochronous in transfer. In means for reading purpose, out means writing purpose. Let's say this is for bulk. Let's say this is for bulk in, bulk out. Just an example. Okay. Now I start one application. I means who? User. As a user, I'm sitting here, I'm running one software. What is software? I open my this one. I go to my here, and I say initiate transfer to one of the pen drive devices. Now what will happen? Let's say that device is this one, device number 12. So my host driver, device drivers will figure out that there is a application level request that is getting initiated to device number 12. So now then it asks itself one more question. What type of transfer is that? Is it a, sorry, is it, what type of transfer is it? Is it a isochronous type of transfer, or is it a bulk kind of request? What is the type of request? Now it will ask, okay, if it is isochronous, only there is only one point, which is that one endpoint, that is endpoint number 1. If it is endpoint number bulk, there are two or three. Again, what is the type of transfer you want to do? Do you want to do in transfer, or do you want to do out transfer? Accordingly, my host will figure out, it schedules a transaction to device number 12. Now, how does it tell that I want to target device number 12? It has got one field called as ADDR, which is a 7-bit variable. So it will assign in the packet it generates, it assign a 7-bit variable equal to 12. So when the packet goes to everywhere, basically USB works in a broadcasting model. USB 2.0 transactions happen in broadcasting model. What is meant by broadcasting model is every packet goes to every device. So there is a token packet. This packet transfers starts with token packet. Token packet, also TP, has a field called as address. So my host will create a token packet with ADDR equal to 12, EP equal to 2. As this packet gets broadcasted, this packet will go to everywhere, but only device number 12, the device which has been assigned address of 12, will recognize that this packet is for me. Other devices, even though they get token packet. They ignore that packet because their address doesn't match with the address that is coming in the token packet. This is why addressing is required. This is why addressing is required. So it is for the host to tell which specific device am I targeting. Is it clear to you?
Yeah, got it.
Okay. Okay, let's come back to the discussion. We are talking about how the host and device communication happens. The host and device communication starts with the user. Who is user? You and me. We will start an application. What is an application? Some software running on top of my operating system. It could be operating system level or an application which is on top of my operating system. Targeting that application finally will target either one or more USB devices. Let's say I start playing a song in an audio player which is connected to USB. So I am targeting one USB device. Let's say I give a print. Simultaneously, I give a print. I am targeting two USB devices, one audio player, one printer. So my host will figure out that, okay, there are two requests now. Now in that it will figure out that, okay, audio player is isochronous in nature, printer is bulk in nature. So naturally I have to give more priority to isochronous. It will create the transactions in such a way that isochronous traffic is given more priority and bulk is given a lesser priority. In some, once this decision is done, the USB host generates frames, either low speed, full speed, either or microframes, either frames or microframes, targeted for all devices. Basically, targeted for all devices means what? All the frames go to all the devices because it works in a broadcasting model. Now, what is, I have been using the terms frames and microframes. What is this frame and microframe? Let's understand. Basically, low speed and full speed communication is done using frame. Frame is a 1 millisecond interval in the USB communication time is called frame. 1 millisecond time. Now 1 millisecond at what speed? 1 millisecond at 12 megabits per second. I mean, if you take in case of full speed, if I take an example of full speed, I'm doing 1 millisecond. So now let's calculate how many bits will be transferred in one frame. Can you do the calculation, please, everyone? See, simple. At full speed, we send 12 megabits per second. So a frame is of 1 millisecond duration. So how many bits will be there in a frame? So how many bits is one frame made up of? Can you please do the calculation? How do we do this calculation? 12 into 1024 into 1024. These many bits per second. So how many bits for millisecond? How many bits per frame? Which is 1 millisecond. So how do you convert this information into millisecond? You have to do 12 into 1024 into 1024 divided by 1000, which will, if you do that calculation, it will come to 1572 bytes per frame. Okay, this is about frame. Same thing if I take microframe. Microframe is used for, so the high-speed communication is done using microframe. Microframe is 125 microsecond interval. Basically 1 millisecond divided by 8. interval is called as microframe. It happens at 480 megabits per second. That is at high speed. So how many bits will be there in one microframe? If you do the same calculations, you will finally come to this number, 7864 bytes. Will come to this number. Frame or microframe. See, going forward, I will be using, going forward, sometimes I will call frame or microframe. Both are used in the same context. So there is no much difference from understanding perspective, from user's perspective. What is that is actually differing is the number of bits and number of bytes are differing, but the remaining concepts are all same. You send token packet, you send data packet, you send handshake packet. That happens in frame also, that happens in the microframe also. So if I'm using frame, don't think that I'm only talking about full speed. I am also talking about high speed also. The frame has series of packets targeted for the connected devices. Again, you have to remember this one very important difference. Basically, USB 2.0, USB 1.0 and USB 2.0 works in broadcast model. Okay, where every packet goes to every host generated, I would rather say host generated packet goes to every connected device. It is the host, it is the device function address that was assigned during enumeration, and the incoming token packet ADDR field matching, which tells whether token packet, whether a set of token packet, data packet and handshake packet is meant for this device or some other device. That is how they discuss. If you go to USB 3.0, USB 3.0 is not broadcast based. It is directed. It is packets are directed to a specific device. The frame always starts with startup frame packet. The frame always starts with a startup frame packet. Startup frame packet is followed by packets in below order, below format: token packet, data packet, handshake packet. Above series repeating for entire frame. So in summary, whether it is frame or microframe, you can visualize it as SOF, comma, N tick token packet, data packet and handshake packet. So you can visualize like this. This total number of bytes adding to either 1572, adding to either 7864. Till that time, whatever happens, you frame or microframe. You understood the point, right? I mean, n can be any number. N can be 1, 2, 3 based on what is my requirement, what is the size of data packet, that will decide n. Okay. So, but overall, this will add to 1572 in case of frame, or it will add to 7864 bytes in case of microframe. Okay. SOF is always generated by host and it is broadcasted to all the devices. It is an indication. It is an indication that a packet is started, a frame is started. Token packet is always generated by host. It is broadcasted to all the devices. That is the indication that some transaction is getting initiated. Now data packet can be either direction. Data packet can be either host to device or device to host. Same thing with handshake packet also. So each packet starts with sync field to help device host figure out start of the new packet. Please read this. So each packet starts with sync field to help device and host figure out start of the new packet. Each packet ends with end of packet pattern. These patterns added by the UTMI. See, UTMI adds a new pattern called a sync pattern so that the device knows that a device or the host knows that a packet is starting. It will add EOP in the end of the pattern for the receiver to know that packet is ending now. These patterns are added at the UTMI level, that is at the file level. Next. We have been talking about different types of packets, right? Let us understand what is token packet is about. Please read this once. So I was telling you that basically frame or micro frame is one startup frame followed by a group of token packet plus data packet plus handshake packets. So how does a token packet look like? Token packet has a packet ID. It is called as packet identifier, which tells what type of packet is it. PID is 4 bits. It indicates 4 bits means it indicates 16 types of packets, right? 2 to the power of 4. And address is address assigned by host to the device. Address used by the device to figure out if this set of packets, token packet, data packet, and handshake packets are for it or for some other device. Endpoint will further tell, once it is for me, in me, which endpoint is being targeted. Endpoint tells the device core which endpoint is to be used for this packet communication. The frame goes to all the devices connected to the host, that is means by broadcasting. USB 2.0 uses address field in token packet to figure out if the packet is intended for it or not. See what USB 2.0 does? USB 2.0 uses address field in the token packet to figure out if the packet is intended for itself or some other device. Let's see. Next is host device communication further. How much is pending? Okay. Let's continue for another 15-20 minutes, then we'll wind up session. There is a buffer concept in the USB 2.0. Let's understand what is this buffer is about. SRAM is used. So first let me explain through one diagram, then it will be easy. So let me take Okay, see now what happens is host is targeting endpoint 1, let's say endpoint 1 out, for example. I mean, host wants to perform a write to this function, and let's say it wants to do isochronous transfer. It sees, it will check which endpoints are. So the question is what? Host wants to perform ISO write to device address 5, let's say. Now host will check which all endpoints in device 5 are isochronous and out based, out direction. Let's say it has listed endpoint 1. Endpoint 1 is, let's say, ISO out. Now what it will do is, because isochronous is, since isochronous is periodic transfer, it needs to be given priority. So host will schedule a token packet. In this, among this series of token data handshake packets, it will create one token packet with ADDR equal to 5, EP equal to 1. Why EP equal to 1? Can someone tell me? Because we want to target isochronous out, and endpoint 1 is the isochronous out type of packet. So this token packet and followed by this token packet followed by the data packet, and no handshake packet still won't happen. Okay, in this case what happens is this token packet gets broadcasted to all the connected devices, every device, every hub and device. Essentially the device number 5 will have this token packet ADDR matching. Then it will check, then it will check the endpoint number. First it confirms, do I have endpoint number 1? Answer is yes. Okay, now so it basically device number 5 will expect to get a data packet from the host, because it knows that endpoint 1 is ISO out. If it is ISO out, I can't give the data, I have to get the data. ISO out means I need to get data, packet. So data packet, host provided data packet will come to device 5. Now what to do with the data? What to do with the data packet? So what device will do? Device number 5, endpoint number 1 is mapped to some buffer location in the internal SRAM or internal memory. This data or payload coming in data packet is automatically means by means of internal DMA is stored into this SRAM location, into this predefined SRAM location. As soon as this is done, as it starts storing the data into SRAM buffer mapped to endpoint 1, the USB 2.0 core protocol layer generates a DMA request to the function controller. Now function controller understands that I am getting a DMA request. So it is an indication that there is a write happened from host to endpoint 1. So how DMA request will come? DMA request will be 15 down to 0. It will come as 16 tick B 00000000000010. This is an indication that DMA request is happening on endpoint number 1. So the function controller means what? Example is what? My printer or music player, any of them, etc., knows that will issue a read request. This is basically addressing the DMA request to the same buffer space where the data is getting stored, and the memory returns the data to memory provides the data to function controller. Essentially, data is moving from host to function controller with buffer, with SRAM as acting as a buffer. Basically, SRAM buffering makes sure that there is no back pressure conditions, no back pressure or bottlenecks gets established. What does it mean? If I'm not able to service, if endpoint 1 is blocked, host will do endpoint number 2. If it is also blocked, it will do other endpoint. It will do transfers to other endpoint. Whereas without buffer, above concept is not possible. Without buffer, above concept will not be possible. This is how this whole thing works. The same thing happens in the reverse manner. Let's say now my host wants to read data from the device. Almost above process almost happens in reverse manner. This is called as in transaction. Basically, all the directions in USB are with respect to host. All the directions in USB are with respect to host. In means the host reading from the device. Out means host writing to the device. So now let's read this. This would be easy to understand now. So what is the significance of buffer in USB 2.0 core? SRAM is used for data buffering during communication with device function controller. USB core uses endpoint to figure out where to buffer the incoming data or outgoing data before it is accessed by the device function controller. If it is not accessed, it is provided. If you are reading from the pen drive, it is the pen drive which provides me the data. It is the pen drive which will write the data into my buffer, and host will my protocol layer will read from the buffer and gives it to host. USB core can support up to 32 endpoints. Each endpoint has following characteristics. It can be either supporting a transfer type of isochronous, control, bulk, or interrupt. It can have either direction of in, out, or setup. Setup means for only control. See, setup is compulsorily mapped to control only. This is the compulsory map. Now these remaining combinations are possible. That means 3 into 2 is possible. 6 combinations are possible. Each endpoint has 2 buffers, buffer 0, buffer 1, which has starting address and size, A buffer is nothing but a simple memory interface which is accessible by both USB protocol layer and the USB function controller. USB protocol layer initiates DMA request to the function controller on DMA request bus. I told you, right, DMA request will be there, through which my protocol layer tells to the function controller that there is some access happening to my memory location on specific endpoint. Function controller identifies the endpoint number. Based on that, it completes the DMA handling. The protocol layer generates 16 DMA requests, one for each endpoint. Function controller keeps track of each endpoint buffer pointer, endpoint characteristics for DMA transfer completion. It keeps track of what is the transfer direction, what is the current buffer pointer, buffer size. Based on that, my function controller knows where exactly it has to initiate the read or write in the buffer. I think we will stop here. I mean, because probably anything more will get a bit exhaustive. We will stop here. In the next session, we'll again revise these things. Probably some of you may not have been able to follow these things. So we will revise these things again. Then we'll go to the next aspects, how the USB core architecture looks like. In summary, what is happening, I'll explain in this diagram. See, the host is giving data. Data comes to protocol layer. It doesn't directly give here. It stores the data. It gives an indication. It goes and reads the data. This is in case of out transfer. In case of in transfers, it sends a token packet with in type of endpoint, targeting in endpoint. So my protocol layer figures out that there is a read request. It starts reading here. In the meantime, it would have populated here. So whatever data I have written here, it written here and it goes here. Essentially, what is happening is a data transfer is happening from here to here. Here to here. In case of in case of out, here to here. SRAM is acting like a temporary buffer for that purpose. So let us talk more about this in the next session. So in the next session, we'll be quickly winding up USB 2.0 because we purposefully we don't want to spend a lot of time on 2.0. We will quickly move to 3.x and then we'll proceed further with 3.x. The point I want to emphasize is everything you discuss for 2.0 is applicable to 3.0. Lot of things, I mean, almost all the things are common. Hence, whatever time we spend, it is as good as learning 3.0 also. So do you have any questions?
Yes, Srinivas.
One second. So you will be sending meeting link for upcoming session. So I mean, I'm not sure whether I will be able to communicate especially after this. So in case, so whatever we had now was a demo session. If you think this session will be useful to you, this is the fee transfer link, and the fee I would have told 9,000 plus GST in the mail everywhere I would have communicated. So you can initiate the fee transfer to this account, and the same link will have one link called as VLSI3.com enroll. So please fill those details. So when you enroll, we will create a WhatsApp group. You will be added to that group. So all the communication will happen in that group. Basically, that we'll use that for technical doubt clarifications. I mean, the session timing notice, session timings, any other things, right? Let's say going forward after 1 year, we get some opportunity related to USB 4 or any USB 3, we'll use that group to post those requests. I mean, it would be one point of communication between you and institute. Yeah, so through that group only we'll communicate everything, the session links, everything. It will be a new link. Whatever today I sent, it is only for today's session. For tomorrow's session, it will be a new link. Any questions you have?
Sir, regarding course content, it is a USB 4 protocol. I understand USB 2, USB 3, and USB 4 will be covered. Only it will restrict to the protocol. Is it target audience for the design side or verif side or PD side? How it will be any verif also covered here?
Basically, we are not going to do much of design and verification activity, because if I try to do too many things in 6 or 7 weeks duration, you will not learn anything. See, even now you would have felt I went a bit fast in last half an hour. If I ask, most of you might have felt that there are a few things I did very quickly. So even if I go at this pace, I'm not sure how much I can really cover in 7 weeks, because there are so many things in USB. If I go to USB 4 again, I have to spend considerable time, right? So to be straightforward to your question, see, to do design, to do verification, anything you need to do, you need to have a good protocol understanding. See, good protocol understanding is the starting point for everything, right? Once you have that good protocol understanding, the remaining implementation is only 20 to 30% of the work. So this course will enable you with that 70% of your learning. Remaining 30% we can do. I mean, if there are considerable number of students, we can also work on design implementation and test bench implementation for USB controllers. But as of now, this 6 weeks course will only focus on USB protocol learning. It is targeted for both design and verification engineers. It will be useful for both of them, because the core thing you need is the protocol understanding, right? Wherever you go. Any other questions?
Yes, I agree. So after learning the protocols session in those course itself, if it is 10% of if test bench coverage is there, it will be helpful. General talk, that's it.
No, general talk can be there. See, but I can't do any coding. See, what is the problem with coding is, once we develop test, we have to develop environment. Once we develop environment, we cannot stop it there. We have to develop agents. Once we develop agents, we have to develop items. Once we develop items, we have to develop sequences, test cases. So when it comes to test bench development, there is no stopping thing that here I have to stop, right? We can discuss the features that need to be part of the test plan, how the test bench architecture can be developed, how the agents will look like, and what kind of sequences can be coded. But I don't want to do much of programming in this course. That can be a separate course.
Srinivas, in your last slide, you have shown the USB 2 functional core architecture. Likewise, do you have any USB 3.2 extended? Anything like, do you have any architecture to explain?
This one you are telling?
Yeah, yes. This is USB 2 functional core, which was available in
we
the.
Can develop this also. I mean, I can explain that.
Yeah, 2 I know, but I just want to know, is it a USB 3 architecture? Do you have that?
3 architecture, I can show it to you when we go to that specific part of the session.
No, I just want to know that if we have, then it would be fine enough.
Right now, I don't have that readily available. See, basically, USB 3 architecture is established through some. We don't have design internal architecture. They show the line-to-line connection between protocol layer, link layer, physical layer. At that level only, we will understand.
Okay, because USB 2, this architecture is available in GitHub. Okay. But USB 3, we don't find anywhere. Only protocol aspects, link layer, as you said, link layer, transponder, those things detail only available. But I don't see any particular design architecture identity for USB 3. So
no, because the point is what? Yeah, please complete. Sorry.
Okay. Yeah. Our institute provide those architecture wise, like we can map it twice. This is, you can, if you show this architecture, we can understand, oh, this is the flow, like in and endpoint goes out. Likewise for USB 3 also, do you have that architecture? This would be fine. This was my expectation.
I can develop that. We can develop that. So the point is, this architecture is not any benchmark standard. If you ask me, is this the standard every company will have Is this how all the connections get established? I would say probably no. I mean, if you go to one company, they may have implemented USB core with some variation. So there is always a variation possible, but we can come up with a generic architecture which complies to all the requirements of USB 3. We can do that.
Okay, because USB 3 are more sophisticated, like data LTSSM, pipe layer, particularly I can say pipe thing. So
Yes.
I expect those things. That's it. If you are covering in our upcoming things, it would be very fine for us.
Yeah, I will do that. I'll include some micro architecture of each layer as well. So probably I believe you are talking about micro architecture of each layer, right?
Correct. This is a whole function, right? Just USB 2, you are showing that the protocol layer also there, and you can see UTMI. These two things are in the a single picture. I just want the single picture for USB 3 architecture.
Okay, sure. We can do that. I will cover that.
Sure.
Any other questions you have?
Srinivas, I have some basic questions again. So you mentioned the frame structure, how it will be like SOF and the packets which follows that. So is there any frame completion? How device will know like frame? I mean, how that
frame is a notional concept. Frame is notional concept. It's basically the host measures everything in terms of either 1 millisecond or 125 microseconds. It is host is only that frame is for our convenience. I mean our understanding purpose. But from a host perspective, it keeps measuring the time. So okay, 1 millisecond elapsed. So one frame interval is elapsed. So as soon as one frame interval is elapsed, it starts a new frame.
Oh, okay. Suppose if I mean this question needs one more thing. What is the maximum data payload size that can be transferred? I mean, this is related to the frame again.
I will cover in the next slides all those things. For every type of packet, for bulk, isochronous, interrupt, there is a limits that are provided by the protocol. We will talk about that in the tomorrow's session.
Okay, sure. So I mean, my question here is, can a data packet be present in 2 frames? Continuation data can be followed in 2 frames is what my question.
Continuation data packet.
Suppose frame length is example 1
no,
millisecond.
it has to be through backend. I mean, it has to be token packet, data packet, handshake packet. You cannot have data 0, data 1 immediately coming without other token.
Oh, okay. Yeah. And one more thing is, you mentioned each device can have 32 endpoints, out of which endpoint 0 is dedicated for control type.
Yes.
So who will decide which other endpoints needs to be like isochronous in, isochronous out?
It is the manufacturer. Let's say you are manufacturing a pen drive. You will decide. See, 32 is not a compulsory thing. You can decide that I will only go with 3 endpoints. Endpoint 0 compulsorily I will manufacture because there is no alternative for me. Endpoint 1 I will keep for bulk in. Endpoint 2 I will keep for bulk out. Why you want to do that? You want to keep your pen drive cost lower. By keeping lower number of endpoints, you will need lower buffer space. You can manufacture probably pen drive at a lower cost. So it is you who will do that, and when you manufacture, you will load the descriptors with corresponding information, which will, when host reads this pen drive descriptor information, it knows that there are 3 endpoints. One is control, one is bulk in, one is bulk out.
Okay, so suppose I mean the endpoint 1 can support both bulk and isochronous. That can be possible.
It is not possible. It is illegal.
Okay, so in that case, like endpoint 0 is dedicated for control, based on the device manufacturer or something, each endpoint will be dedicated for its own transfer type.
Yes.
Okay. Yeah, got it. And what is the role of processor here? Because descriptor read should be happened through processor, or host will do that too?
Host will do everything. So it is the processor will talk to host. Host will initiate every other, all the other aspects host will take.
Oh, okay. Yes, thanks.
Any other questions?
Yeah, I have a question where like how the endpoint buffer space is mapped to particular address space in functional memory or functional core,
It is
function core memory.
decided at the manufacturer level. So basically, when someone is manufacturing the device, the manufacturer knows how much buffer space do I have in this, and how many endpoints do I have. Endpoint, let's say I have 3 endpoints. I will map endpoint 0 is anyway mapped to my registers only, descriptors only. Endpoint 1, I will map it to this much space. Endpoint 2, I will map it to this much space.
Okay,
So it
in
is
that case,
the
like if I have like function core memory as like 1 GB, then total endpoint space should be all the endpoint buffer memory space should consider 1 GB.
no. See,
Right.
you should not confuse function core memory with the buffer memory. Buffer memory is different from my pen drive memory. My pen drive may be 1 gigabyte. That is
Right.
not this buffer memory. That is different. So it is internally the manufacturer will decide, I believe, how much buffer space to use. That he will divide it into different endpoint buffer spaces.
Right. What I am saying is like if it is static mapping, like if
Yeah.
one endpoint or one buffer space is can be configurable to different address space, then it is we need not have higher buffer space. Like if it is not configurable, then we should keep all the functional core space in buffer space also, right? Is my question is clear or?
No, not exactly. See yeah, you can come back, but let me give you my explanation.
Okay.
The way I look at it is that during manufacturing, the manufacturer hard maps. He does the hard mapping of specific endpoint to specific buffer space, so which we won't be able to change as per my understanding. So hence that is mapped. Even the function controller exactly knows where exactly this endpoint buffer corresponds to. Now please tell me your question.
Okay, so let's take we have two buffers, two endpoints which map to two buffers.
Yeah.
Okay, and these two buffers are like in endpoints only. Like all the data comes to this buffer, goes to the out buffers, which goes to the functional memory.
Yeah.
In that case, like if I have 1 GB functional memory,
Yeah.
then if first buffer space is like around, both are not considering 1 GB, then how it will be mapped? Like if it is 0.5 GB in one buffer space, that will be mapped to functional memory. That should be that way, right? If it is not 0.5 GB, one. So if it, let's take only one buffer in the device, and that
Yeah.
buffer is mapping to the functional memory. Should be mapped to the functional memory.
No,
Whatever
every
we
whole buffer is anyway finally mapped to function memory only. The whole intention of
right.
buffer is only for function memory, right? There is not.
So
What else do you think our pen drive will do? Does it do anything else other than interfacing with function memory? It is only for that only. It is just
right.
that you are dividing that buffer space across multiple endpoints.
Right. So here we have only one buffer. So
Okay.
all the like it should be of 1 GB length, right? If it is less than 1 GB, then how it will be considered the whole functional space?
It need not be. It won't be so high. First thing you need to understand is 1 GB is a very big number you are talking about. This won't be in 1 GB terms. It will be in few megabyte terms because it is just a temporary storage. As soon as you start writing, you start reading. So hence it need not be the size of my actual pen drive.
Yeah. So when it is reading from the buffer, it should be copied into certain address space in the functional memory.
Yes.
Right. How that address is defined,
It
like
is the
from the
function
buffer
control.
to which?
Function controller also knows what endpoint corresponds to what address of the SRAM.
Okay.
Both protocol layer also knows endpoint maps to which location. Function controller also knows. Through that they know what exactly which location you have to target.
Okay. So it is like whenever the host is sending data, if it is like there are in between if it is like in the functional space, if it is of 1 GB, out of
Yeah.
1 GB, like maybe some partition it want to access and it want to write some data into that partition.
Yes.
It will, what it does, host it does, it just transfers the data to the buffer endpoint buffer.
Yes.
And from that buffer to partition should be decided by functional
function control
core, right? Function core. So here, function. How does function core knows that host is targeting certain partition?
It knows because as soon as the transfer comes and it starts writing, it initiates a DMA request to it. Right. There is a request, one kind of request goes through that. It knows that there is something happening to this specific endpoint. Let's say endpoint number 3 is there. With endpoint number 3, some request will come here.
Okay, right. That only indicates that data is being written from the host to, and data is ready in the buffer basically.
Yes.
That doesn't indicate like where to copy or where in which partition or which partition it wants to copy.
It knows. I told you, right? It knows because both of them are mapped. Both of them knows the information. Like this also knows what part of thing endpoint 3 corresponds to. This also knows what part of the memory endpoint 3 corresponds to. It knows that from here only I have to start reading.
Okay.
It's like someone came from outside the institute and he kept something in one of the rooms. I know where exactly he's going to keep. So I will go and get the data from that place only. Because we both have talked already. The other person who is coming and keeping the information here, and I also, both of us know where he's going to keep that information. Okay. So any other questions? Okay, we will end the session here. Tomorrow's session will also be at 9 o'clock. Please note, it won't be a demo session tomorrow. If you plan to enroll, please let us know by today itself, and you can initiate the transfer and enroll. Yeah. Thank you.